Morning, everyone. This is Sudeep, your host for this AI Pathshala by KTech Center of Excellence for Data Science and Artificial Intelligence, which is a NASCOM body, and IFIM. I have Professor Chandrashekar from IFIM, who's one of the senior professors out there. Let me first give a small introduction about Professor Chandrashekar. He's one of the top analytics professor in the country right now, and he has been the chair and the officiating director at Ford School of Management, New Delhi. And he has also been a senior professor there. He has headed several software development functions that saw building of prototype of products in the areas of business intelligence, risk management, and customer relations management. Professor Chandrashekar holds a PhD from University of Georgia, USA, and a master's and a bachelor's from IIT Kanpur, and has a vast experience of over 34 years in R&D, academic, and industry in the area of quantitative techniques and IT. He teaches courses in the area of IT, quantitative techniques, text mining, sentiment analytics, advanced market research, and so on, and worked worked as a chair of quantitative and information systems group at IIM Lucknow for about 10 years now. He's a member of the IIM Lucknow board for about 3 years, and he was also a visiting professor at the Manchester Business School for about a year under the Euro-India exchange program. I mean, the more I speak, it's less. There is so much to cover about Professor Chandrashekar. He has got several awards as well. To name a few, he received the NASCOM Devang Mehta Award for the best teacher in the year 2010. Apart from that, Times of India Education Times Awards for contribution to the area of IT 2013. And he's also regarded as one of the most remembered faculties at IIM Lucknow by IIM Lucknow Alumni Association during their Silver Jubilee celebrations. So with that, I welcome Professor Chandrashekar and the rest of the participants. Today's topic, so today is actually the part 2 of the session which we did on 5th of November. And those who have joined before, welcome back again. Those who are new to this session, welcome again. So I'll just set some ground rules before I hand it over to the professor. So as you can see in your Zoom window, there are 2 options. Number 1 is chat, and number 2 is Q&A. So if you have any questions directly for the professor or any doubts, you can put it in the Q&A. Chat is, if you guys want to talk among yourselves. Now, we start the session now, and at regular intervals, we'll have Q&A sessions like the previous format which we did. So if you have any questions, you put it in the Q&A box out there. Currently, everybody is muted, since it's a webinar format. The participants would be muted, but don't hesitate to put in your questions in the Q&A. Our first break would be at 11:30. It will be a 15 minutes break, and we start exactly at 11:45. Post that, again, a Q&A at around 12:30. Another Q&A at 1:15, and we close approximately at 1:45. This is going to be more of a hands-on session. I've been part of the session with Professor Chandrashekar last time. So it's more hands-on, just keep listening. And I know Professor doesn't believe in too much of theory. So he'll quickly take you to the tools and, start explaining. So with that, I hand it over to the professor. Sir, over to you.
Oh, yes. Oh, yes. Oh, yes.
Good morning.
Good morning to all. Thank you, Sudeep, for the excellent introduction you have done. I think all our participants, I think expectations would have gone up. I will try my best. Today's topic is computer vision. In fact, when I was in Department of Space, I worked at that Space Application Center in Ahmedabad and also National Remote Sensing Agency at Hyderabad. So at 35 years back itself, we did all this. So that way, this topic is not new to me. So what used to happen at that time was this data was not that democratic. So Google Maps were not there. So if you want to publish or write anything, you have to take permission from 4 ministries, like Ministry of External Affairs, Survey of India, Defense Ministry, and then I think one more. So most of the work we could not publish. Otherwise, there is nothing much new in this. That way, ISRO handles more complex images than what our normal participants will handle. Most of them will handle only color pictures. So that way in ISRO, what happens apart from these color pictures, we get data from the microwave sensors also. They are a little bit difficult to handle because there is no RGB there, and it is a microwave reflected energy that comes, and there are some lags in that. So you'll have to do lot of pre-processing there before we overlay a microwave data and a visible data. And also we get data from different heat sensors, which is much more different than what you see in the visible band. Probably some of these heat sensors and other things, probably when these IoT comes up, some of those devices you get that type of data. I think probably with that IoT proliferating apart from our visual data, which is in my view, little simpler to analyze compared to the other two, and overlaying those two data along with the visible, I think that's what will be the future. Because you can't expect all sensors to acquire data only in what the human eye sees, what we call the visible band of the electromagnetic spectrum. We have an infrared band, we have ultraviolet band, we have X-ray band, we have MRI band, which is used in medical images. They are much more complex. So today's talk or today's demo and other things, we will restrict it only to the visible pictures, that is your color pictures, which you take from your mobile or some other devices. Maybe at some other point in time, as and when this technology becomes diffused to more and more users and more IoT devices start coming, then you get the other two types of data also, something in the form of ultraviolet or microwave sensors. For example, in non-destructive testing of your welds and other things, you get infrared and ultraviolet type of data. We are not going to break the weld and then find out whether something wrong is happening or not. Then the part itself is broken. So you get those type of data also. And something from microwave, particularly when the 5G technology comes, some of those type of data you get apart from your usual picture or what we call the visible band data. So that's what the total picture is. Ultimately, in 1 or 2 years, I think more and more data types will come. And thermal sensors will take data in the thermal band, because in night, if you want to observe anything, obviously the visible band does not work. You don't have sun there wherein you can take a picture. It is all dark night. So in the dark night, if you want to see whether some enemy is attacking your territory or some drone is flying somewhere on your territory, it has a lot of defense implication. So you will have to go for the thermal band only. We take what are called the thermal images. Thermal images characteristics are a little bit different, and microwave image characteristics are a little bit different. And our visible picture, yes, it is little simpler to handle. That's what I will cover today. We will restrict it to the visible band. Then I will use that our open source tool called 9. Last time also, if some of you have participated in the text analytics class, I used 9. It is an open source software, fully open. It doesn't have any expiry or those type of things wherein some other companies will say, for example, if you take RapidMiner or Head2O.ai, they work for 30 days, then you will have to take a decision what to do with that. Again, if you try to download second time, sometimes it says this IP address you have already downloaded, etc., etc. All that will happen. This is fully open source. It doesn't have an expiry. It is from end to end, right from that data cleaning, pre-processing, usual statistics, reading data from big data environment like Hadoop, Spark, SAP, and some of these ERP systems. It can also read data from SAS, that is our SAS files. It can read about 30-40 different type of files apart from our image, video, audio, all those files it will read, PDF, all that it will read. So that way it is very, very versatile. It is hosted on the cloud also. You can use the cloud environment. Otherwise, you can freely download it. The current version is 4.2. What I am using is 4.1, except that they have added a few more modules. It has a huge community, about 30,000 users. Community is there, so that even if you get stuck or put a question, since the community is very large, some response you will always get. Within 24 hours, somebody or the other will respond, though NIME may not respond. There is a service also, if you buy, they will respond any query within 18 hours or 12 hours, like that, depending on the time difference. NIME stands for Constant Intelligent Mining Engine. That is what that NIME stands for. The headquarters is in Switzerland. There are about 9,000 to 10,000 users of NIME. India also has a small NIME group. About 300 or 350 members are there in that NIME group. We hold what is called that Open Data Science Conference, that is called the ODSC. This time ODSC will be held in Bangalore, I think in December 8th and 9th. And NIME also supports these ODSC seminars. If some of you are interested to learn something more about these computer vision, text analytics, you can attend that ODSC seminar. It is of course online this time. They hold east, west, all those things. There is a lot of sharing of information that take place. One thing about NIME is it is a workflow based software. For example, if you take Excel or SAS or SPSS, they are called menu driven software, because every time you will have to go to that menu, file, open, insert a function. That's a menu driven software. So next time if you want to do it for a different data, you will have to repeat this whole menu again. You will keep on clicking those things only, unless somebody writes a batch file or a VB file and then puts it in a batch and runs it. All will not be able to do it. It requires a lot of IT expertise. Whereas NIME and then SAS and these rapid miner H2O.ai, all these are workflow based software. So what it means is you write the workflow. Once the workflow, you make it work. Second time when you change the data file, you don't have to touch the workflow at all. It automatically runs the entire workflow. And if you want to do it on more than one image or large number of times, you put all of them in a folder and simply execute it. The entire data it reads and then analyzes. That is other benefit of what we call the workflow based software. That way NIME is a workflow based software. It's not a menu driven software. Coming to this computer vision, it has a very strong pre-processing part. What happens is most of the time, some of them do not have much background about the images. The tendency is to put everything. We normally do not pre-process the image much. We simply dump that entire image and then build a convolution or some type of a neural network which has something like 15-20 layers. Eventually it takes about hours to distinguish between a cat and a dog or something like that. So the basic reason that happens is Pre-processing is very important for the image because the size of the images are very large. So I will stress on the pre-processing first, so that it saves your lot of time, and also the accuracy will go up. It is something like dumping both good data, bad data, everything into your neural network and trying to say, you please give me accurate classification, how it will do. We mixed both bad apples and good apples and trying to tell them, give me only good, nothing works. So in the pre-processing stage itself, if I remove something like 40-50% of bad apples, then the next stage becomes easy. So the common mistake that is made in image analysis, we don't do much of pre-processing. As a result, we get screwed up in the later stages. First part. The second part is the analysis of computer image networks becomes extremely complex if you do not do pre-processing. So what happens is your execution time becomes very large. And nowadays, the tendency is to analyze the data in real time. So in real time, it becomes very difficult to execute these complex, what we call the convolution, neural net and other type of neural networks. So the best thing is do the pre-processing. Then you will save lot of your time, efforts in the final outcome. Then we have something called edge computing. That's where your real-time analysis, if you want to do, we keep something called an edge computing device, and that we run all these in the real time. So edge computing devices and your edge servers are not your full-fledged servers. So obviously you can't operationalize a full-fledged image processing system on that. One method to transfer it to the edge computing is do the pre-processing. Then obviously your execution time comes down and you will be able to analyze images real much faster rather than simply building more complex networks, and eventually it takes hours to identify. So pre-processing is an important step in the image analytics. So if you can take care of that, almost 80% of your analysis you took care. Eventually you don't need so complex networks to do if the pre-processing stage is done. So that's what it is. I will show some PPTs because some of you may not be very much familiar how an image is handled. And I will touch on mainly on the application part. Some of you are attending today the webinar. If you are interested to modify the existing algorithm or develop new algorithm in computer vision, then what happens is all of you have to brush up your knowledge on what is called linear algebra. It is not your normal algebra, not that quadratic equation, those things. There is something called a linear algebra which forms the basis of image analytics. That is matrices, operation on matrices like finding an inverse, eigenvalues. How do we extract information from a matrix? Because your picture is a matrix. It is a two-dimension array. So it becomes a matrix. Now what happens is when we take sequence of pictures, you will put one picture behind the another. And if I want to identify a moving object or something, then it becomes a stack of pictures. So already 2 dimensions are there in one image. Like that you keep stack of images one behind the another. So it becomes a stack of 2-dimension images. Mathematicians will call it a tensor. This is what is called a tensor. So we have a separate branch of mathematics called tensor mathematics. Very few, I think, education institutes teach in my country. One reason is, I think they could not find a large number of applications where tensor comes. That's why we did not, that's why not many teach. But with the image analysis and observing the motion picture sequence of images, yes, they become tensors. I think eventually institutes will start teaching what is called the tensor mathematics, which is an extension of linear algebra. So some of those who are trying to work in the product development area, of image processing or computer vision or whatever it is, I think you will have to take a basic course on that, what we call that linear algebra to some extent, and if possible, the tensor mathematics. So without that, no, you will not have foundation at all. You just virtually get lost what these strange neural networks are doing inside. So if you want to understand what happens within the neural network, and this is what is called an explainable AI. One criticism of this deep learning and AI and neural type of network is, unfortunately, the end user, he feels, how did this neural network take this decision? Can it explain? No. Right in this present technology, we are not able to fully explain. That is because we don't have too many people familiar with linear algebra and tensor mathematics. If someone is familiar with this, he will easily write this part of the code, because internally it is stored as tensors. So somewhere I will have to extract that information from that internally stored structure to a structure which our management can understand, which our directors and MDs can understand. That can only be done if you have some knowledge of linear algebra and tensor mathematics. Otherwise, you will not be able to do it. At least please study those courses also. If some of you are trying to modify or improve the existing algorithm, make it more speed, increase the execution time, those type of things, yes. In fact, the name TensorFlow came from tensors. What is it? The name itself gives it TensorFlow. What do we mean by TensorFlow? Tensor is a mathematical structure and it flows within the network. That's why they named it as TensorFlow. That's how the TensorFlow has come from Google. So the basic foundation is TensorFlow. And some of these startups who are trying to develop some new techniques of image classification or image pre-processing, where not only visible data, the other data also comes. It becomes 4 or 5 dimensions. Because your normal picture data is 3 dimensions, RGB, red, green, blue. Plus, we will add a time dimension. If it is a sequence of images, we will get one more data in the form of a time. So it became 4. Then your microwave data is 5. Your heat sensor data is 6. Plus some other metadata, if it comes along with that, it becomes 7. And apart from that, if you want to overlay that meteorological data, that comes in a different format, it became 8. So you will be analyzing 8-dimension pictures, not 3. That's why it becomes a tensor now. So unless you learn it, for those who are doing in the product development, yes, they need it. But as a user, you don't need it because somebody else has taken care of that part. I think that is briefly about it. I will just show some little bit of PPTs so that everyone will get some background. There are no mathematics in those PPTs because if somebody wants maths part of it, you, of course, our Sudeep knows my email. You send me an email. Those type of course material I will send. Little bit of your linear algebra and something about this tensor mathematics, that I will send. Because this is start as an elective course in our PGDM MBA program, same computer vision I call it. It is a 30 hours course total. All our courses are 30 hours. All our PGDM courses are 30 hours. In the 30 hours, I am spending about, it is less actually, about 6 to 7 hours. I am spending it to teach these linear algebra and little bit of tensors, because without that they get lost. So those type of material, I can send it to those who want to a little bit go deep into this and understand what it is. So that's what it is. I will just show some PPTs on the basics of how an image is captured and how do we represent it within the computer. Up to that I will go. Maybe afterwards, I will again go back to this NIME, show some pre-processing steps. Then again, I will stop and introduce little bit of neural network and what is this deep learning, what happens within those deep learning layers. Then again, I will come back to NIME. So what happened was I wanted to show this TensorFlow, but somehow, I don't know, this name got updated. It had some auto update. Last time somehow it updated to 4.2 and that Python also get updated to some 3.9 version or something. For your class demo purposes, I had made the workflow there that back end of Python was 3.7. And immediately today morning when I opened this worksheet, it stopped working virtually. Some Python version incompatible, all and all I came. I didn't want to struggle with that. So what I have done is there is an alternate backend that is called Deep Learning 4J backend. It is a Java backend. So TensorFlow and then Keras, they are all front ends. What happens is at the backend, it runs a Python code, nothing else. They are only your user interfaces, nothing else. So,
Professor Chandrashekar, sorry to interrupt. Just want to check. Hope you're not sharing anything because it's not visible yet on the screen.
Just a minute, I will share the screen. Sure.
Yeah, yeah. We'll just test that out so that.
Oh yes, we will test it out.
Yes, it has come. It's visible. Maybe you can go to the presenter mode.
So shall I start?
Yes, sir, you can start.
Shall we make this full screen?
Yes, make it full screen.
So what happens is all your Keras, TensorFlow, etc., they are the front-end interface. At the back end, it runs a Python code. So now somehow there was some mismatch in that Python, I think version or something.
Sir, your video has gone off. If you can try that.
Hello?
Professor Chandrashekar, your video is not.
No, somewhere it got lost, so I didn't want to touch it here, thinking
Okay, okay. Let me check once.
Anyway, during the break, I will bring it back.
All right, sure.
So,
sure.
On your TensorFlow, Keras, TensorFlow is more of programming. So somehow they found it is very tough to program. So they put a front end called Keras. Keras is also not that much simple. Compared to TensorFlow, it is simple. But eventually, they all run a Python code in the backend. Now, our NIME provides other backend also, that is the Java backend. So we have the Deep Learning 4J, that is called Deep Learning 4 Java interface. That I will be using for my demo because that's working. So what all that happens is your Keras front end and the DLJ, Deep Learning Java front ends are the same. So the screens will always be the same, whether you use Keras or TensorFlow or your Deep Learning 4J. 4J stands for fourth generation, then Java interface, Java backend. The front end screens are the same, except user even doesn't see the difference between the two, except that name comes. Otherwise, there is no difference. So we have that classical demo of pattern recognition. If I use normal pictures, it takes a lot of time, so I am not using it. So what the demo I will show is, we will classify the digits. We have digits from 1, 2, 3, 4, 5, 6, 7, 8, 9. These digits are captured as the JPG files. It is some 24 into 24 picture we have been captured. So we will train a deep neural network and classify these images, classify these numbers. Number classification also is equally important. If you want to extract the digits from a number plate of a car which has been captured on a CC camera, you have to extract the digit. And if you take something like medical application, assume that somebody who is very much old aged or someone, he takes his blood sugar level on that blood sugar meter. You will see numbers like that, 139, 142, like that. So if I can extract the digit part alone, I can send it to the doctor. So that way the digit identification is also very much important. That demo I will show it to you. I will show it using the Deep Learning 4J integration. And same thing happens with the Keras, except that your icons will be different. Otherwise, it's the same thing. We will try to classify the digit. Same thing, you can use it for picture classification also. On the Kaggle, you have about images of that 40,000 animals. Most of these animals are there. Same workflow, I will send it after the class to all the participants. You just play around with that worksheet and try to classify the images of these animals. Similarly, what you can do is, whoever has time, you can download all those images from our Amazon or Flipkart site. You have all those fashion images and other things. Download some 1000, 2000 images, classify it. And then when somebody uploads a new dress as an image, if that exact dress is not there, I will classify and give you the closest matching dresses during that. That is another application as an exercise. I will leave it to all the participants who are in today. So learn the workflow. First, learn the workflow using that Kaggle data set of animals. What I will be showing is for the digits, because it is little faster and it doesn't take much time. I will show it for the digits. You do it and validate your workflow on that standard cat dog. It is called cat dog data set or something which is available in Kaggle. So you develop the workflow. Now what you do for your specific application, now you don't have to touch anything. You simply download all those images into an HTML file or an Excel file. In the Excel file, you give the URL of the image on where on your hard disk the image is stored. And the second column on your Excel sheet will be the class. You can call it fashion 1, dress number 1, dress number 2, dress number 3. Like that, you collect that 1000 dresses or TVs or mobile phones, whatever it is. So you will have 2 columns in your worksheet. One column points to the image, the C:/ wherever you have stored it in the image as a JPG file. The second column will be the class, to which class that image belongs. So you give it to your workflow, it will do it. You are not changing anything now, no change. You can do it for TV images, you can do it for mobile, you can do it for other images. So first try it on that. I will show the demo for digits because that is little bit simpler to handle and it takes less time. And the other thing is, even though we call it hands-on, I was not very sure what is the configuration of your laptop and other things. That's why I did not tell today to download NIME and then come with this. It takes some time. It is about 900 MB file. So you will have to download NIME, and the minimum RAM that is required is 8 GB RAM. But what they recommend is 16 GB if you want to do serious this computer vision type of work. If you want to do that normal statistics, decision tree, classification, etc., 8 GB is good enough. And for text analytics also is all right. Somehow 8 works. But for computer vision and image related work, what they recommend is 16 GB RAM, so that you don't spend. Otherwise, it takes a lot of time and you are not very sure whether if something is working or not. That is the recommended configuration. So when I show NIME, I will show you what all additional modules you will have to upload, you will have to download to run Keras TensorFlow integration. That I will show when I go there. All the PPTs I may not be able to explain. What I will do, some minimum I will explain. These PPTs also, I will mail it to Sudeep as a link. All of you can download it. There are few more PDF files, some introduction to convolution, neural network, those things that you can study. One or two sample, there are about 4 or 5. Pre-processing, I have about 3-4 workflows of 9. Then classification, I have 1. So I will mail all these 5 workflows. What you do is, instead of my image, you put your image, download some image. There are a lot of images nowadays on many sites. Almost all e-commerce sites have images. So take some real life image, not simply cat and dog, which is available in Kaggle. No, 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 no. Take some real life images like furnitures, TVs, fashion dresses, or your other things, real estate, or pictures of your flats and other things. Classify it. So rather than simply using that cat and dog, that one. So image processing, image pre-processing involves acquisition of the image. After we acquire the image, what happens? Image is an analog signal. Whether it is your camera or something, it is an analog signal. Analog signal our digital computer anyway cannot understand. So somewhere what we do internally, we convert this analog signal to digital signals. So that's how it becomes a digital image. So the digital image is represented internally as numbers. So what happens eventually, what you see inside the machine is a series of numbers. So that's how your digital image gets represented. So image has two coordinates. One is the horizontal coordinate. The other one is the vertical coordinate. Because each point on the image, I will have to point out. So obviously it will have two coordinates. So if it is a black and white image, yes, you see only black and white. So either the, and different shades of gray. It will be somewhat more white, less like that. So if it is a color image, you will see all sorts of colors on that. So what we do in pre-processing is when you take an image from different sites, you would have got images of different sizes. So when we train a neural network, it expects all the images to be of same size. So one image may be some 1024 by 1024, another image may be 256, another image may be some 52 and all. No, 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 it cannot work. So we will have to standardize the size of these image to one standard size. That is one part of pre-processing. Then sometimes you will have some noise in these images because these are captured by devices, or some analog signals or some external disturbance will be there. So obviously any picture without noise, it is too difficult to obtain. You will never get. So the first step in pre-processing is how do we remove this noise? Because noise is an unwanted information. And when you train these pictures with noise, eventually your computer will make a lot of mistakes also. Because most of the time your noise may overtake what is actually present in the picture. And what do you classify a noise? It is a random picture. So you will say object not found finally. What it means is whenever you get some type of a message from these image processing systems telling that image not found, probably it is not that image not found, still the image will be there. But unfortunately, the meaning of that is there was too much of noise in the picture, so I did not understand what is the actual content, so I am classifying the noise. So when once the noise is classified, yes, definitely it will say I am not able to find any features. So if you get those type of messages, that means you have not done the pre-processing properly. If you have done the pre-processing, those messages should not come. No, no, no. Why should it come? Because unfortunately, it could not identify. Then sometimes what happens is there are some shadows in the image. So that shadow obscures the actual content part. So we will have to somehow remove that shadow effect. That is another pre-processing. So standardizing the image to bring it to one size, removing the noise, what we call smoothing of the image, the second part. The third part is correcting for the illumination and other things. Somewhere that shadow would have come, you will have to remove the shadow. And another one, and the next pre-processing is somewhere what would have happened is in one picture, you would have looked straight into the camera. Then in the second picture of yours, somewhere you would have tilted your head or something. So that means there is a rotation in the picture. So, but it is actually you only. But unfortunately, if you do not correct it for the rotation, our computer takes it as a different person altogether. So this is called what we call the transformation for rotation. So that is another pre-processing you will have to do. These are major 4 pre-processing steps in the other image. Then the color image comes in 3 channels. What happens is any color, it is the basic Newton's law, which says that any color is a combination of 3 primary colors. So red, green and blue you combine depending on what is the intensity of red, what is the intensity of blue, what is the intensity of green, you see what is on your screen. So it is a combination of RGB. So the moment you see any color picture on your screen or your own screen itself, the computer screen, internally it is stored in 3 images. Internally it is stored as 3 images. One image is for the red content of the picture. The second image is for the blue content of the picture. The third image is for the green content. And when we digitize the image, that continuous signal into digital, all of them are digitized to 0 to 255 scale. So that is how you see most of the color images. So your red intensity will be anywhere between 0 to 255. Blue intensity will be anywhere between 0 to 255. And red intensity will be anywhere between 0 to 255. So what happens is, if your red intensity is 255, blue is a 0, green is a 0, you get a full red picture. And in the other way, if blue becomes 255, R is 0 number and B is 0, you get a blue image on the picture. So any image is a combination of all this. That is the basic principle all of you should understand. And since image is 2-dimension, it can be represented internally as a matrix. That is the mathematical structure of an image. Matrix in 3 planes. That is how you represent the image. And images take large number of space. You just say you will call it 1K by 1K. 1K means they are 1K, 1K points on the X direction. And on the Y direction, you will have 1K points. So 1K into 1K will become 1 megabyte. And 1 megabyte into 3 colors, it will become 3 megabyte minimum. So your minimum 1 color picture is going to take 3 megabyte. So if I have to analyze 20,000 pictures of cat and dog, you just see what it became. It became 20,000 into 3. Some 60,000 megabits and all it becomes. So it is a very large volume. It's not like your text and numbers. See the volume. And even your mobiles nowadays comes with 40 megapixel camera, 10 megapixel camera, like that. That means each picture is taking 10 megabytes. So you see the volume, it is highly voluminous. That is why unless we do pre-processing, what you will classify, if I give you 20,000 images of cat and dog, and each image takes 3 megabytes, virtually you will have to search through your 60,000 megabit data just to classify one cat and dog. No, absolutely no way. It is. That's why I was telling pre-processing is very important. You just understood the volume now. The volume of picture compared to your text and other things. They are nowhere. Getting a database with numbers of 60,000 megabytes is virtually, it takes years to get that type of data, whereas some 20,000 pictures of cat and dog occupied that large space. That's why they recommend large RAM to be there in your machine to analyze images. Otherwise, lot of swapping will happen. We keep part of the image, throw it back to the disk, again bring it back, throw it back. That's why it takes a lot of time. There are 2 methods of pre-processing the pictures. One is called the spatial domain, or what we call the normal domain, X, Y, Z. The other one is called the frequency domain. Those from engineering background are a little bit familiar with this. What we do is, in non-technical terms, we convert this X and Y picture into some sort of frequencies. So in the frequency domain, we do the analysis, then convert it back to the time domain. That is what we call the frequency domain methods. I will not be teaching this in this class because this becomes a separate class altogether. And it has a lot of advantages. It takes less space. We can compress your picture in the frequency domain very efficiently. We can do high pass filtering. We can remove the noise very easily and very short time when it goes to frequency domain. I think in future, most of these computer vision software may use frequency domain techniques rather than these time domain techniques, because when the picture becomes large, it has certain advantages. Sir, any question answer? Can you?
Professor Chandrashekar, I just put it on chat, asking participants if they have any questions.
Yes, yes.
Most of them are requesting that your video should be on.
Just a minute.
Can you go down to the bottom of your screen?
Just a minute.
Yeah, sure.
Start video.
Yes, yes. You are visible now.
Okay, okay.
And I have got one question from Anil Kumar, who is asking how to set threshold value to remove noise.
That will become clear when I show the demo. We do something called an histogram equalization that gives me a threshold. We have a technique called equalizing the histogram. So I will take your original picture. Original picture has some type of a different histogram. So what we do is we equalize. So looking at the histogram, I will fix the threshold. Or there is an automatic way to fix also. In fact, internally, it stores the histogram and does some type of a moving on the threshold, observes the picture. And then wherever we get less signal to noise ratio, that is the threshold.
Sure. Any other questions from the participants?
So far,
sir, we'll give it a minute. If there are any questions,
sure. Yes.
Then you can continue.
It doesn't have to be on this. If any other future thing also they have any doubt, that is fine. It doesn't have to be only on what I am showing.
Absolutely, sir.
They can ask other things also. It need not be only this. Next 1 to 1.5 years, I wrote in my that note also, this computer vision field has a large growth. Huge amount of money and budget is spent on this, and particularly with this contactless boarding, there are a lot of places where these images have to be used now rather than pre-COVID. I think all of us know it has speeded up our digitization. So in the process, picture is also speeded up. Your images are also speeded up, not just documents. So particularly on this contactless boarding, where without touching anything, you get down from your taxi and board to the aircraft. It uses images in many places. That is classic application of image recognition, and it will speed up the boarding process also. And in non-destructive testing, welding, how do you know that after 1 minute of weld, something has gone wrong? And it is that one only, we capture that infrared images and trying to tell that welding person, please stop it, something wrong is happening, there are some holes that has come up in the weld. Otherwise, presently what happens is after you weld and it goes to some testing at the QA stage, he says, no, we are finding some holes here. What does he do? He has to break the component itself. So in the non-destructive testing, yes, this comes last. Take textile itself, these automatic textiles, you know, your cloth comes at 5 meters per second and 6 meters per second. How do you visually inspect whether some process has gone bad? And by the time that operator recognizes that something is going wrong, and you would have manufactured hundreds of meters of cloth, I will have to throw everything now. Whereas this image analytics, at least I will be able to reduce the waste. I may not be able to, instead of wasting 100 meters, I will waste only 10 meters now. That is other one. And these robots also, if I have to tell a robot, pick that 1-inch bolt, 2-inch bolt, 3-inch bolt, how does it distinguish? I will have to put all of them in a box and then say, pick up that 1-inch bolt and put it here. It has to identify that 1-inch bolt. So there is no text here. It is a picture only. So it has innumerable applications, and I don't know, even If you look at that Gartner report and all, they say some few $1 billion is being put in this image and computer vision type of work. So it has a large growth, and my advice to all these youngsters who are attending this webinar today, please concentrate on that more. Rather, your usual job you continue to do, but at least for the future, something you have to plan. So this is one area where a lot of research is going on, where a lot of new products are coming. Most of the startups are working in this field only now, because this field is what is left out from long time. Our classical RDB database and all, we have reached saturation there. There is nothing much to do. They have all reached almost the limits.
I mean, I don't have any questions, but one Rajmani M is asking, what would be the best platform for basic courses in linear algebra, TensorFlow, and tensor mathematics, image analytics?
Correct. Sir, what is happening? We have this IIT Madras. They have started that BTech 4 years program in computer science or data science, something. They have put some course material on that open platform. That is one. The second one is edX. We have that edX, you know, that open source
right
learning. It is not paid. At least Coursera, what happens is, for some of the courses they charge. All are not open in that Coursera. edX is there. Then you can go to that MIT site. MIT site, mathematics department. If you go that MSc course outline, you just see there they put this linear algebra and tensor. It is not normally taught at the bachelor's level. No institute teaches at the bachelor's level. That's a master's level course. I think there you will be able to find it. And I can send some material, because what I am teaching for my students is also basics only. They don't come from maths background. Most of our MBA students, they are from commerce, they are from science and physics, chemistry, somebody hotel management, like this. So for him to learn this, yes, at least the course has to be basic. So
sure.
That I can send. That is not a big issue.
Sir, I think we can continue now.
Yes.
Screen your presentation.
Sure. So there are two domains. I will just expand this one. How do we go to full screen here?
Sir, at the bottom.
It has come.
You're there. Yeah. So we are seeing image enhancement on the screen right now.
Correct. That's the correct slide. Yes.
There
are about 30 of them. I will just cover few and then leave it. Then it becomes a full PPT type of lecture, which I am not keen to do it. That's why.
Sure.
I will just give some background, so that when I do the demo, some small fundamentals at least has to be there. Otherwise, they will find it difficult there to understand. That's why. So frequency domain, we have Fourier transform. We have something called a wavelet transform. We have something called a Laplacian transform. These are the three transforms. And for picture, we use Fourier and then the wavelet. They are the two transforms that are used in the picture. NIME has that module. It has both Fourier transform module and it has the wavelet module. So you can take the wavelet transform of your picture, and then some small front end has to be written for that, some small code. Then your rest of your other thing works as it is. There we don't distinguish between frequency and this, except that convolution part has to be a little bit changed. And the advantage of this is it is faster. Analyzing images in the frequency domain is faster compared to the time domain. In time domain, as an example I can give, if it takes about 30 minutes to analyze that picture, when you go to the frequency domain, you virtually analyze it in 10 minutes. And if your code is efficient, you should be able to 1:4 or 1:5 is what the speed you will get. And the size also gets reduced very much. 1:20, 1:30 compression it gives when I store the picture in the frequency domain rather than in the time domain. This is what it is. XY is the coordinate. So what happens is, in every digital image, it has a horizontal coordinate, and it is a vertical coordinate. Then what is the gray level at that is what is the picture. See what happens is on the screen, if you take 1k by 1k, that is 1000 x coordinate, 1000 y coordinate. So I will say there is a point on the screen whose coordinates are 255 on the x-axis, 750 on the y-axis, and you see a value like 120. So what it means is, on the screen, you move horizontally in units of pixels, what is called a 1 point element. 1 dot is something like a pixel on your screen. So you move 250 dots on the horizontal direction, 750 dots, you move it on the vertical direction, and I put a number like 70 or 80. So what it means is that 80 is the gray level. So if it is a black and white picture, 0 is black, 255 is white. So this 120 or 110 is something like a gray type. Now if it is a color image, you will see 3 values. So the x coordinate, that is x pixel, it is 250th pixel on the x direction, something like a graph sheet, and 750 on the y axis, and you see 3 numbers like 127, 64, 200. So what it means is the red intensity of this picture is 120, the blue intensity is about 67, and the green intensity is 200. So when you combine these 3 intensities, that is the approximate color you get on the screen. So these are called the gray levels. So the picture is represented as a matrix. That is what he has written XY here. And T is a transformation. So what it did is that analog signal, it digitized and then grew and then converted it to an integer between 0 to 255. That is this T function he is writing. T is a function which converted that analog signal to a numeric signal. That is this T. Fourier I have already covered. These are all the frequency domain pictures. You can see here some pictures we have shown. Some noise is there in the first picture. It doesn't have much noise. I will show you the noisy picture. There it will become more clear. Image restoration. See here what we do is somehow the image is either too much blurred or we are not able to see much features in that. We try to recover as much picture back as possible. That's called image restoration. Somehow we will make the picture more sharper. Edges should become sharper. Noise should be removed. That is called the restoration part. This mathematics part, you leave it. Anyway, noise will be there in the picture. We will try to reduce this noise and some type of a function we apply so that the degraded picture will become as much as possible. That's fine. And in fact, this was my PhD thesis itself about 30 years back. In 83, I got my PhD. We had the satellite images collected at ISRO. We had a classic problem. What happens is they are visual images collected from our remote sensing satellite. What happens is during the monsoon, I get the cloud. And below your Ganges is flooding and Brahmaputra is flooding. Then on the picture, I get a white patch. So how do I reconstruct this river course back? That is image restoration. So that we can move all these people along the bank and that rehabilitation can be done. Image restoration, because unfortunately at 800 kilometers when I take the picture from the remote sensing satellite, cloud has come in between. So what happens eventually is I will see a white patch. Cloud is white, bright picture. So below Ganges is flooding, Brahmaputra is flooding, and your sea is flooding, or that sea coast is changing. And when I look at the picture, I am not able to identify where are the river course. So we try to reconstruct the picture back. That is your restoration. In fact, that is my PhD thesis itself. That's what I worked on, these remote sensing images and tried to construct where your Yamuna or Ganges or Brahmaputra takes a course during the monsoon time, depending upon the rain. whether it is heavy monsoon, light monsoon, or intermediate type of thing, we try to reconstruct the picture back. That is your image restoration. We try to reconstruct the picture back. These things, wavelet I have covered. This part I will leave. These are the major pre-processing steps. Compression I have told, we try to compress the picture. That we do using the transform. These are all the pre-processing. We extract certain regions in the image, certain shapes we try to identify in the image, boundaries. So these are all the operations we do. These are all pre-processing of the image. We call dilation, erosion, open and close. If I have some time, I will explain. Otherwise, I will show it on the picture itself. This is what it is. See here, dilation and erosion. See what happened? We shrunk these white areas. So when I shrunk the white area, these big areas became small and these small areas vanished. This is one way to remove the speckle in the image. See what happened now? You had large rectangles and this noise is something like a speck. It is a speck. It is a small pixel or 1 to 2 pixel size. So what happens now is I compress this rectangle. So when this rectangle is compressed, since the size is large, it remains. And this fellow, since the size is very small, it went. Then I will reconstruct the picture back. Again, I am expanding, so all these dots get removed. This is called the dilation. So what we do, we shrink the large areas. When I shrink the large area, these small fellows vanished. So this became small, it's all right. So in the inverse transformation, what I am doing, I am expanding them back again. So I got the picture back. So these dots have gone. That is called the dilation and then erosion. This I will show on the picture itself. See here, instead of these 3 dots, we got some type of a shape of that. Instead of doing that individual pictures, I know there is something called a curve that is coming. We extracted some type of information from these 3 pixels, that there is some type of a curve that is going there. We identify different segments in the image. We detect the lines. Line detection is very important. If I want to identify some large number of railway network or road network, they come as a linear features, though not exactly linear, it is more or less linear. So that is where we use. And even to identify the airports, that's because your runway is linear. So what normally happens is, if you want to identify some airport in your enemy territory, you take a picture, satellite image or a other aircraft image and identify linear features. And I will put a rule there telling that any linear feature is greater than some 100 meters and less than 300 meters and no trees on both the sides. Probably it is a runway. This is how we use the linear feature to convert it to some type of a strategic strategic input to either defense or some other place. Yet detection. What happens is, I see your picture. I cannot analyze each pixel and then try to classify whether you are X, Y, Z. So what we do, we identify the contours or your edge, your face edge, distance between your eyebrows, distance between your lip and your eye, distance between your lip and your nose. These are called the features. So during the convolution neural network, this neural network will extract the features. And it is the features we store. We don't classify the image like each pixel taking and trying to classify. That becomes massive. Because I gave you an example that 20,000 cat and dog, it is some 60,000 mega bytes will be there. How can you classify each pixel to say whether it is a class or a dog? No, we can't do that. So what we do is, we extract some type of a feature. So that's what I said. For your face, it may be your distance between the eyes, lip and the eye, something like a triangle, it becomes lip and the nose, and your hair and then your nose. These are the features we extract. That feature is what we keep in the machine. And then when the new picture comes, we extract these features and then compare it internally, and whichever is the closest match, we classify the picture. That's what it is. And another caution I would like to give is, no classifier is 100% accurate. If somebody comes and tells you, sir, I have classified with this neural network, 100% it is classifying. No, somewhere he has made a mistake. There is no technology on the earth today which can classify the images 100. We have reached up to 85, 90, that's all right, no 100. And most of the time our students, in an enthusiasm to get marks, sir, 100% classification accuracy. Then you ask him to show your demo, he is out. He will say, that is not working, this is not working, I will show tomorrow. Somewhere he wants to skip because he knows that he never got 100. So there is nothing which gives you 100. 80, 85 is good enough. So that is where we detect the line. Line is very important to identify your railway network, then your road network, particularly in inaccessible areas. And if you want to deliver your health and other services in inaccessible areas, how do you approach them? Through this map only you can approach. Or where do you want to construct a new road? How do you enter there first? That's what it is. Thresholding is what somebody was asking. So we use the thresholding to remove the noise in the picture. Both white pixels as well as dark pixels, both of them we can remove by changing the threshold. There is something called region growing. We start with some small pixel in the region and keep on growing it. And somewhere when we reach the edge, where the gray level changes very much, we stop region growing. This theoretical part, I won't be able to cover today. Then it becomes equivalent to full day course or at least 2-day course. So we will not do it, but I will show you on some pictures how it looks. Color and texture. Texture is very important. See, what happens is, particularly in the agriculture data classification, when I take the picture from the top, your sugarcane crop and the paddy crop and some other crop, all of them look green. So they have high green intensity. Now, how do you distinguish between a sugarcane and the paddy field? Because when I take it from that 800 kilometers or even from an aircraft, which is about few kilometers from the ground, only you get both of them are green. So there what we do, we compute what is called the texture of the image. This is another dimension you have to add. Texture is something like how coarse or how smooth is that picture. So I will have to add this texture. Then only I will be able to distinguish between the sugarcane crop and the rice. Obviously the texture is different. See the size of the leaf. So your rice crop has a thinner crop, leaf, and whereas sugarcane, it is very broad. So if you simply look at the image, you will see both of them green. No, you will not be able to classify now, it will misclassify. So what we do, we compute what is called the texture of the image. So this part I am not able to go deep into this. But for a layman term, it is the standard deviation of small window within the picture. How much variation is there in the texture? So the texture for a sugarcane crop will be different from texture for a rice, and it will be different texture for tomato, like that. So that's how it will be very much useful in your agriculture classification of images. And in textiles also, some cloths are very smooth, some cloths are a coarse structure. So if you add this structure apart from your image, compute this structure, add it as one more dimension in your data, then build a classifier, you will be able to classify it accurately. That is what we mean by texture of the image.
Professor Chandrashekar, there are a couple of questions.
Let me clarify, that is easier. Yes.
Yeah. So Sheetal is asking, you spoke about 9 dimensions. Would you clarify what we would cover in this course today, and is it only RGB image?
No, I don't even have those type of images. RGB okay. Is what we cover, and I just said as an example the problem they may face in real life in another 1 year or something, when these IoT devices and other devices start sending those type of images.
Right.
Right now, we have only in
Another
defense,
one.
defense and airlines, they have these type of images. Already they have.
Sure. Right. So another person, Shravani, is asking that can you tell that 9 dimensions?
No, not dimension. What I said was, it is like this. What normally happens is you will have one color picture which have 3 visible bands. That became 3. Then your thermal image will become 4. Your time dimension, if I have to identify a moving object, it has a time dimension. It becomes 5. Microwave will become 6. Your weather data, all your wind speed and other things which you see in your weather map, normally on your TV screen, you see some weather pictures, all that humidity, wind velocity, all that. So you add them, it virtually becomes 7 or 8 now.
Sure. And there's another one from Monish who's asking, can we increase the accuracy by setting up values of hyperparameters?
Correct. See, that is the other way of doing. What I am telling is, yes, hyperparameter I will cover later on when I show the demo. What I am saying is, instead of doing all that marathon exercise, take care of that in pre-processing stage. Virtually, those will come down now. You don't have to search so many parameters now. And in the process, what you are doing, you are making the network highly complex. That is because you did not do pre-processing much. If you do pre-processing much, all that hyperparameter tuning and taking that 30 hours to classify 20,000 pictures, I will bring it down to 10 hours without making the network complex. And the benefit I get is, particularly in the edge servers, we cannot run a full-fledged TensorFlow and Keras network there. It doesn't have that capabilities to run. So how do you implement this type of technology to analyze real-time images? That is my issue. See, if it is not real-time, yes, you take 1 hour, you take 2 days, and then you go and tell your boss, after 2 days, sir, I have classified. That is not what we are talking. What we are talking is, how do we put this technology to real-time use, where it has much use? There this needs. So the pre-processing can be done on computers, even with 16-bit computers, 16-bit CPU chip I can do. Whereas a complex convolution neural network, you can't run on a 16-bit machine. That is the problem.
There is another one, sir, asking how can, or can you, okay, how can you set threshold value to remove noise?
I'm showing it in the demo. Ask them to
Sure.
wait for a while.
Sure, sure. And one last before you continue.
Yes.
What technique can be used to remove the clouds? We face the same issue in some other research problem.
Cloud is by threshold. It is a white picture, you know. So what happens is, that's what I showed. Cloud is a large region. Shrink the region. That's what I showed, the dilation exercise. Shrink and then expand the other part. After you shrink, it becomes very small. Identify it as a segment, small segment, it becomes a small segment. Remove that small segment by segmentation. Put a segment limit on that. Something like 30 pixel by 30 pixel circle, or something like a rectangle that bounds the cloud area. We will give a rectangular shape for that. The dilation will shrink it to a smaller area. Then what we do, we say, okay, the rectangle of 20 pixel by 30 pixel, probably I don't want it. Other features are larger. So remove it. Then the cloud is gone.
Sure. Sir,
binding rectangle. We put what is called a binding rectangle on that. And filter that. And in the frequency domain, it becomes simple. Since I am not touching that, I am not going into that. That's why I stress that part, that some of the advantages you have in the frequency domain, I don't have to do all these exercise. It is very simple. Put a high pass filter. It immediately throws the cloud out.
Sure, sir. Over to you.
Okay. Good. Some pictures, some questions are there. This part I have covered. All these applications I have covered. And medical images takes much more complex. Your MRI, CT scans are, they are much bigger than your RGB pictures. Resolutions are very high. and there is a separate standard to store these medical images. Not many software can read it. NIME can read medical images. It can read your CT scan. It can read MRI. There is a standard, I am forgetting the name. That's how all these medical devices store the picture. Some MID, some standard is there for images. It can read. It can read. And many times you get some noise in your X-ray CT scan because that instrument generates a noise. Some person moving or some other body holding a mobile phone, and even if he goes 10 meters from that your MRI room, sometimes it picks up those things and then puts it as a white spot. So pre-processing specifically for medical images has to be done. Because your size is very large and we have to be very sure 100%, we can't have some 85% classification accuracy there. No, that is not acceptable at all. That is much difficult type of training the network, because they want almost 99. They don't want this 85 and all. 85 is all right for agriculture images. So to identify a person or to identify your dress, what you like, it does not matter whether it is this way, that way. Not in your medical, those type of applications. That I am not touching today. But what I am telling is the pre-processing is compulsorily there. You have to do it. Otherwise, no. Your classification accuracy will come down like anything. Radar, sonar, robotics, all these where images are used. I have shown some of them. I will show on the actual data. Don't worry. I think that's it. Another small PPT, let me show. It has some little background so that it gives them. No, this we will cover afterwards. This is about CNN. Fingerprint recognition. This is another application. This is your brief black chart of your computer vision. Most of it I have covered. That's why I am not repeating again. This is our good old method. Either we write the code in Python or R. R is not useful for images. R is useful for your normal statistics. So don't attempt to write codes in R. Virtually you will be out. What you can do in Python or Keras or TensorFlow in 1 hour, you will end up in doing 20 hours in R. Don't put your hand into R there. For particularly computer vision, no R. Or you can use it for standard deviation, mean, mode, regression, decision tree. Yes, that it works. And number of updates in R is less nowadays. Most of them are going to Python. That way Python updates and contributions are much higher, because this field is coming up. More or less your statistics field is more or less saturated. ANOVA, MANOVA, multiple regression, time series analysis. Most of them are already there. You don't see much development there. This also I have covered. This is what the final picture is. Acquisition, pre-processing, segmentation, analysis. Eventually you recognize the pattern. On the left hand part you can see here, it has gone through different stages, and eventually we found this object here, which is not very clear here at all. See here, that's what it is. So we use neural networks because somehow our brain also does some type of a nonlinear transformation. That's why our linear regression and decision trees you won't be able to use much there. So that's why we use that some type of a nonlinear network to classify images. And the nonlinear network is a neural network. That's why it is called, we use that one. When I come there, I will briefly tell. I have covered this. Red, green, blue, I have shown. This continuous signal we sample. All of you know your classic Fenton's theorem.
Professor Chandrashekar, I think the students are not able to see the slides. It's still on the CNN slide.
You share this. I have put this slide share.
Can you slide share the entire screen? Then it will be better, easy to flip through screens. Just stop sharing.
Stop share.
and then share again and say entire desktop.
This one?
Share screen.
That's what I have done now.
Share screen and entire desktop. Or
Now it is coming?
Yes, sir. It's yes.
Okay. So the sampling you have to understand, because your original signal is a continuous signal. What we do is we sample that signal, and then that is the digitized signal that goes. In your mobile also same thing happens. When you take a picture in your mobile, it is an analog signal that is captured in the mobile. There is an A to D converter within your mobile phone, what we call that camera chip. That camera chip converts that signal to an integer between 0 to 255. That is this quantized picture, what we are seeing. This gives some sampling rate. If your sampling rate is very small, you get this picture. It all gets broken, and this is the picture you get. It has to be twice the frequency. That is your Shannon theorem, which it says. There is a certain rate that is already built into your hardware. So I am just showing, if you do not sample properly, how it looks like that.
Professor Chandrashekar, can you go slide share mode? Yeah, bottom of the screen slide.
Shall I expand this one? Full
yes,
screen?
Sir, yes, sir. Yeah, full screen. Perfect.
This is the quantization. You just see here it became totally white, and here you are seeing more details like this. This is your quantization, what we call sampling. When you sample at some 8 pixels per second or something, this is the image you get. When you sample only 1 pixel per minute or something, that's the image. That means your details are getting lost. But the penalty you pay for this is the size grows up. That is the thing that happens. Somewhere you will have to have a compromise between the size and the resolution. This part I will show in the demo itself, shrinking all this. And another thing is, we do a lot of these neighborhood operations on the pictures. So to compress the image, what we normally do is the center pixel. You take one up, one down, one left, and then one right. What I will do, I will replace this intensity with the average of these 4 intensities. That means virtually I rescale the picture to 1/4. So what happens is some detail get lost, but at the same time it reduces your size very much. Here we have taken 8 neighbors, 3 plus 3 plus 2, 8. So what normally happens is there is a center pixel here. Now it may have value like some 140 or something, and these will have different values. So what I will do, instead of these 8, I will put this center pixel, that value, and then these people are gone. That is how we smooth the picture. And this is what your convolution neural network works. That is what he calls a kernel. This is called a 4 kernel. This is called 8 kernel. The window size. So what normally happens is, these 8 is gone now. So instead of these 8, I am going to put 1 here, 1 pixel, which is the average of these 8. Or it can be median value of these 8 pictures. Or we can give different weights for these 8 pictures. Something like 2, 0, 0. Then again 0, 2, 2, 0, 0, 2. So that means this pixel will be multiplied by 2, value into 2, 0, 0, 0, 0, 0, 2 into this, 0, 0, and that's what I'm going to put here. So when I process this picture, these original 8 pixels, actually it is 9. So instead of 9, I am going to get a single pixel here. This is what we call the convolution in mathematics. What we do is, we take these neighborhood values, we replace it by some weighted average of these values. So in effect, what I did was, I reduced this size, and at the same time, when the pictures are large, when the regions are large, you don't lose too much. That is the basic theory in this. Just a minute. This is how the histogram looks like. This I will show you to you. This is how it is. So somewhere most of your gray levels are around this 100. And if you want to remove some white noise, what you do is put a threshold above this 160. Because above this 160, hardly I have only 1% of the data. You see here, hardly it is 1.5% of the data. So these are nice. So roughly what you do, somewhere around 160, you put a filter, all these white pictures will get removed. Then come here again, somewhere around this 60, you put the other threshold. These small people, I am not that much keen because majority of your data is in this range. Since majority of the data is in this range, put a threshold. This may be roughly around 175 or something is the upper end, and put some 60 or something in the other side. Then what happens is I am concentrating on this part of the picture. That is what somebody was asking. How do we put a threshold? You compute the histogram of the picture. This is called the histogram. That is the gray levels. So in the histogram, I can identify approximately where your 99% of the data gets covered. See, roughly this region is almost 99. These regions are nice. So if it is a black and white picture, these are black, these are all white. And somewhere below this are all black. So what I will do, I will put a lower threshold of around 60. Then I will put an upper threshold of about 170. Then this picture is what I will take in the middle. So that is good enough for analysis. That's how we fix the threshold. This is nice. This I will show on the real picture. You see here a lot of these white noise. So when we do the pre-processing of removing the noise has been removed in this. So these white dots you are not seeing here. I will show it on some real data. Here it is all scattered. It is little simpler. Whereas if there are too many dots here, some dots you cannot remove at all. Still we have to keep it. That's what happens. This is what we call the contrast enhancement. If the histogram range is very small, after removing the noise, we stretch the histogram level. That's called histogram equalization or something called contrast enhancement. This is the original image where you don't have where the contrast is poor, and this is where it has increased the contrast. This is called histogram modification. What we do, we remove the noise first. After removing the noise, we stretch the gray levels by some transformation. It can be either a linear transformation or it can be a non-linear transformation. So this picture has been converted to this picture. This is only the inversion. Black has become white, white has become black, and somewhere I can identify the edges faster than in this picture. See here, almost edge only has come. So this is called the inversion of the image. This is smoothing. When you smooth it, what happens is the noise also goes away, and at the same time the picture also becomes smooth. That's what it is. The clarity will reduce. This is what we call a uniform filter. I will run it on the data using NIME. Some data, some pictures I have downloaded. So I will show it on that picture. Then you'll be able to appreciate how it runs, what type of setting we have to do in those nodes, and how it works like that. And this is what we call a Gaussian filter. This is very important. This Gaussian filter, median filter. There is something called Sobel filter. There is something called another convolution filters. I will not be able to teach all of them, but at least on a picture I can change some of them and then show you to the effect rather than teaching the theory part. Then it becomes conducting a full-fledged computer vision course. It will take about 20 hours like that. Thresholding, this is what I said. Remove this is the threshold. So all these black people are gone. This is what I said in my earlier thing also. See here different thresholds. This is my picture. When threshold is 200, you get this type of picture. When threshold is 128, you get this. When threshold is 50, it is totally different. So using the histogram, we can decide the threshold. One is manual, but in NIME itself, if you click that auto, then he will decide the best threshold. So you don't have to do it, but you can see the histogram after the threshold and original histogram. So like that, you can also learn how to fix the threshold. If your particular software or if your particular tool which you are using, it may not have auto features, then you will have to put the threshold. NIM has is a different story. It does not mean if some open source you load from some site, it may not have all this. He will expect you, he will say, please put the threshold like that. So that is how it is. This shows 3 pictures, how the threshold varies. Histogram based, this I have briefly covered. Sometimes we split the region and then merge the region. That is how we got the segment in that image. This I will cover. The edges. This also I will show you using an edge detection filter. How do we get only edges from the picture? When once I get the edge, I can compute all these distances between the 2 eyes, between your lip and the eye, between your hat and the eye, between your lip and the nose, your neck and eye. These are the features of the image. Along with this contour, normally we put a rectangle around this and then store. Otherwise, these curves, suppose you turn your face, this curve may become a little bit different. So what we do normally, we put a binding rectangle on this, and within that we put these features. That is how internally your convolution neural network, in fact, extract this one only. Your CNN extract this from this. So what I was trying to tell was, if you can detect the edges by pre-processing, then your convolution neural network life becomes very simple. That's what I was trying to tell. This is edge detection. Virtually, it has detected the edges. 3D vision and dynamic vision we will not teach in this course. It is a little bit after you understand this first, then we will go to that. This part I will leave. Fingerprint is also comes under your image identification. It is little simpler because it is a black and white picture. It has only 2 levels. Where your ink is there, where your ridge is there, it becomes black. Where the other one is there, it becomes a white. So I can convert this fingerprint to a black and white image. It is not an RGB type of picture. So we will be able to compress the fingerprint faster. And certain features like moment of inertia of the fingerprint, the principal axis, that we will store. That's what is internally stored. Some distance between ridge and valleys. That's the feature we extract from the finger prints. Sir, shall we break for a while?
Sir, yes, I think it's time for a break.
Correct.
15 minutes break, come back at
11:45. 11:45 will come back.
And I can see there are some questions. So after you come back,
we will address that before moving further. Otherwise, somewhere they get lost, and there is no point in. We don't want this talk to be one-way traffic. We want it to be two ways.
Absolutely.
Sure.
So participants, we break now and we come back at 11:45. Thank you.
So at first level, we create the segments, and then some segment you will have to put a limit. Less than that, either a rectangle of this many pixels or a circle of this much or a bounding box. Then we have to filter those boxes. That is how it is done.
Right. And probably I'll ask Mugdha to rephrase her question once again. Maybe we'll give it a shot. There is another question related to the best platforms for basic linear algebra. I think you have already answered edX and MITx. So this is good. How to calculate features? Manjari is asking.
To calculate the features, what we do is first we do the pre-processing. Then the processing part, we use either that edge detection or convolution neural networks and identify the basic edges and segments in the image. Once we identify the segments, then there are various ways: area of the segment, location of the segment, the size of the segment. These features are specific to images. So feature to a face is quite different from feature for a dress. So what happens is that particular object or something has a feature. That's what it extracts. It depends on the feature actually. If it is a pant or something, you have the length, you have the color, you have the waist size, they become the features. How long it is, they become the features, and it is extracted from the image. And that is what I will use it to classify that as
Sure.
size XL or X or small S, L, XL, extra large. That is how we do it.
Got it. And there is another one, sir, asking what is the latest research on medical image classification? Can you suggest a scope of research in this area? This is
The research in medical image is, yes, they wanted to speed up. The second thing is that noise removal, almost they want 99, 98% accuracy. So what I think the research part has to take care is how do we improve different pre-processing techniques, especially for medical images. That's what it is. Sometimes they are exclusively for that. And the type of noise varies from instrument to instrument. So the type of noise you get from MRI will be different from an X-ray, will be different from another CT scan. So what happens is, it is like this. These data scientists or that computer engineer or whoever it is, we will have some idea about that equipment. So probably these are multi-discipline teams, wherein the other side tells you what type of noise is created when the temperature becomes very high. Is it AC related problem, or is it somebody moving with some object or a metal near the CT scanner? So what happens is the intensity of the noise will be different. So when you see a picture, you know what type of noise it is, and during the pre-processing stage, you put those type of filters before it goes to the doctor.
sure.
You don't print that image. See what I am saying? You have an operator there. Some MRI technician will be there, or X-ray fellow will be sitting. Somebody will be sitting before it goes to a radiologist. He will not dump that picture directly. They will come only once in evening or once in 8 hours. So the person's job is to do some type of a pre-processing. So what should happen is, after we develop this algorithm, this can be shifted to the equipment itself in the form of what we call that application specific integrated circuit. These are called ASCIIs. You hard code this algorithm and eventually it goes. Or the second time is we use some type of a fast graphic processor like that NVIDIA, and then implement the pre-processing not in my normal CPU. You implement it there.
Sure. Sure. Sir, another question, which is the best classification algorithm as per your view?
Classification, what happens is, in the image, we do the pre-processing. Then what we do, we aggregate and finally get some type of a feature extracted from the image. From that, we normally use another fully connected neural network, or it can be a decision tree also. That classic classification only we use. Our challenge is, how do we pre-process the image, remove the noise, extract the features? That is what your vision part is. When once that is done, internally the feature is stored as some numbers, as some vectors. Now when once it became a vector, it became usual data like any other data. So we use our classical classifiers. It can be support vector machine, or it can be your decision tree with that ADA boost, those type of what we call the ensemble of trees, or it can be your other classification. Classification part is not changing. We use the same existing classifiers. The challenge is this pre-processing, and how do we, the size of the images are very large. How do we increase the operational efficiency and try to do it in real time? That is the issue. When once I convert this picture to an image, to a number in the form of some compressed vector, then from that point onwards, we use our classical techniques like discriminant analysis, decision trees, fully connected neural network, recurrent neural network, they will come at that stage because they can handle numbers. So I have to somehow convert this picture to a number. That is what is happening in this pre-processing stage.
Sure. Sir, one last one before
Sure.
with the demonstration. Dikshita is asking how many types of thresholds are there and how many can we use?
Oh, no. Threshold depends on the picture. There is nothing called how many type of threshold. See, your digital picture, the range is from 0 to 255. So you find all sorts of numbers between 0 to 255. Normally, the noise will become two extremes. So if you think the histogram is normal distribution, you compute the average intensity of that whole image. Take the average of all the pictures, compute the standard deviation. From the mean, you move 2 sigma on the positive side and remove all the pixels above mu plus 2 sigma. You remove that white type or bright pictures, bright noise will go away on that. And from the average, you go back in the other direction, that is to the left. You compute mu minus 2 sigma and remove all that. All those black dots and small pepper, what we call the salt pepper noise, it is called. It goes away. And what I am trying to tell is you don't have to manually select, our tool can decide. And if you want a manual mode, you can select the manual mode and put these thresholds. And you can play around. What you do auto first. Let it decide some initial guess for you. Now you know the auto. If you are not very happy with that auto threshold, play around, little bit, move it to the left, little bit, move it to the right. Then you get the threshold.
Sure, sir. Sir, we are good to continue and you would have to share your desktop again.
Correct. This one, you know.
Share screen and entire desktop.
They are able to see this?
It's coming up, I think.
I have put this 9 workflow.
No, sir, nothing has come up yet.
What do I do now?
Just go to share screen once again and entire desktop or entire screen. What option you can see?
Just a minute.
Or yeah, share screen and then left top hand corner, you'll see screen. You click on that, it will share your entire desktop.
This one.
Yeah, share.
Correct.
Yes, sir. I can see one.
Now they're able to see?
Yeah, now we are on the NIMES platform.
Correct. So before I go to this workflow, I will tell a little bit of NIME. This is your area where you build your workflow. Now here in the top left hand corner, you see a small box here. Whatever workflows you have developed and saved, all of them will appear here. These are called the nodes in NIME. You see here, these are all called the nodes. Each node will perform a specific function. So we keep on joining the nodes. When once these nodes are joined, it becomes what is called a workflow. So workflow is what are the process you have to write, like you write the process, read the image, split the image, whatever it is, something like this. Split it into different channel, all this. These are called the nodes. That nodes are available in this NIME. I will show you where that node, there is something called node repository. Under this, all these nodes have been saved. What you have to do is you hold this mouse button and then move that node here. I will show you afterwards. Move this node here so it gets there. Then within the node, you will have to set some settings in the node. You open the node and then do the setting. That's how we do it. Then here what happens, I will show you, there is something called NIME Hub. In the NIME Hub also there are a lot of pre-built workflows. You can go there and download some of them. And there are some example workflows here. Here. double click. So when you double click it, it takes you to the NIME site after you download NIME. So it takes you to the NIME site. They have organized either statistics wise, visualization, deep learning, text analytics, like that. These workflows have been arranged, and they all start with a code. 09 means deep learning tensor, 010 deep learning 4J, 03 decision trees. So like that, the moment you see the first two characters of the code, you will come to know to what it belongs. So a lot of examples are there in this. Now I will show you some of them. When you come to file, all these are very clear to you. Import a workflow. So what you can do is, if your workflow is stored in another folder, not under that NIME project, you can import it. Export the workflow. So this will allow you to export the workflow, and the extension is KWF. That is the extension. NIME workflow KNWF. That is how these workflows are saved. It can be opened only by NIME. You cannot open it by other software. As a graphic file also you can save it. That is, it will save it as an SVG. There is something called workspace. So under the workspace, all your project will be stored. So the moment you download NIME, he creates a default workspace called local or something. So under the local, all your data, workflows, and your other things, all of them will be saved in that. There is something called preferences. In this I will tell you afterwards, because what happens when you install Python, when you install TensorFlow, and when you install Keras, you will have to set up what is called an environmental variable. So either you go to that Conda, if you download all this through that Anaconda. So Anaconda has a project manager called Conda. So you go to Conda prompt, and from the Conda prompt, you will download your TensorFlow, you will download your Keras, you will download your Python. So somewhere on your disk, all these have been put. So for NIME, you will have to tell which folder where you have stored these Keras, TensorFlow, your Python and other libraries, all the Python libraries, that NumPy, Scikit, so many libraries. So that is called an environmental variable. I think the environmental variable you can create either using the pip command in Python after opening the Python window, or the simpler method is you use Anaconda. He downloads all the necessary software. It is little simpler for you. And within Anaconda, you go to that Conda prompt. That is what is called the module manager of Conda. So there is a way to set up the environmental variable. After setting it up, you tell this NIME that this is where my TensorFlow is located on the disk. This is the folder where my Keras is located. This is the folder where my Python and all the libraries are located. This is the folder where my Java is located. That you will have to do. Then only you will understand. Otherwise, it will come out in the log file and say Keras module not found, TensorFlow module not found, and something like Python module, it could not locate. All that messages you start getting. That means you have not set up the environmental variable for NIME, which is used by these modules. That comes in these preferences. Install extensions. There are a lot of extensions in NIME. I will just click and then show it to you. There are so many. It will first look what are all the extensions that are available, so that you don't have to load it again and again. These are the major extensions. Big data extensions. Here you get all these Spark, Hadoop, all those, and your MongoDB, your NoSQL databases. All of them will come here. This extension is basically for biometrics and other things. Medical images, some of them are come here. These two. And this is what you will have to load. There is something called image processing and analysis. You will have to click this and then go to next, and next it installs. Since I have already installed, I will remove this click. Otherwise, we will waste another 15-20 minutes in installing. So within this community extension, if you want to know what are all the modules, click this. All this is there. Image processing you will have to install. Image processing deep learning extension also you will have to install, so that your Keras and other things will be able to use the pre-processed images of your image extension. Again, this is for Java, this deep learning 4J. So if you want to run it as a Java backend, instead of some two hands are there. What are they? Deep learning 4J is for Java, and this is for Python. So if you want to run your Keras and TensorFlow, the Python extensions have to be installed. Python, image processing, Python. KNIME Labs also has so many extensions. Active learning, audio processing to read your audio files. This is your time series. Arima, deep learning Keras. This has to be ticked. There is something called deep learning Keras, TensorFlow. These two you will have to click when you want to use TensorFlow as a backend. This is Java, deep learning, 4J, Java integration. Most of them run on 64-bit chip. Don't use your old, that 32-bit Intel chip. Most of these extensions will not work at all. So all this you will have to download before you run my sample workflow, which I mail it to you. You will have to load all these extra modules. See here, this Apache is also there, Spark. This is your H2O. This is another open source. It's not that fully open as 9. So if you want to pass on some pre-processing, H2O is not that strong in image analysis. They are strong in your text and other things, normal. So if you want to use some of the modules there and then integrate it, you click this H2O machine learning integration. JavaScripts also you can put. Spotfire, statistics, so many extensions, Tableau. You can take some of the results to Tableau back. And it has no development tools also. There is a software development kit. So with that software development kit, you can either modify the source or you can write your own nodes if it is not already there in 9. And you can contribute to the node community also. Or some nodes are available in node community. You can download those nodes also. There are huge number. That is what it is. This is the main menu. So whatever you want to install, you just click it and then do it. Since it is already there, I will not click this one. I just showed you how it comes and how to install these updates. Without these updates, no, this workflow will not run. Your usual statistics and then visualization, line graph, P graph, ANOVA, multiple regression, decision trees, all of them will run. Not this image processing part will not run here. Close this one. There is something called preferences. So here you come to preferences, you see some menu like this. Put here. Now this image processing plugin, something called this Python deep learning. When you click this Python, this is where you will have to click this path. See here, my Anaconda is in my C:users.ifim called Anaconda 3. This is what you will have to set up. Because when you have downloaded Anaconda to your machine, somewhere you would have installed this Python folder there. This is the path. This has to be set. This you will have to do it for Keras also. This is called the environmental variable. So what you do is you go to preferences, you will get all this. TensorFlow, you get the click here. Whether you want a GPU to use or CPU to use. So if it is GPU, you will have to that NVIDIA. Otherwise, it will put it to the CPU. Since it is already there, I am just cancelling that. But first time it goes through. You will have to put this apply and then close. This is the button. You will have to click. Then it will apply and then close it. That's how you put the preferences. That's where it comes. These are all preferences. You can have more than one workspace. Suppose you are working on more than 4 or 5 projects. So what you do is you can create separate workspaces and then put all those workflows in that workspace. That is your others means these other work. This is the default. KNIME workspace is the default workspace. NIME creates when you install NIME. So you can create your own workspace. Group number 1, group number 2, group number 3. So like that, project number 1, project number 2. When different groups are working on different projects, you can create the workflow. This last one is update KNIME. So what happens is this is version 4.1. So you click this update, he will automatically update to 4.2. But somehow you will have to be a little bit cautious, because when once this becomes 4.2, this is the problem I faced in the morning. I think my Python or something, it was a different version. So one workflow stopped working, telling that some incompatible with Python, some environmental variable could not be found for that new Python. I think he was searching for some 3.9. It created, I had only 3.7. So these new workflow started looking for 3.9. Since I didn't want to take a risk, I did not do it for you. That is where it is. So this is the basic menu, this is the workflow. Now this is the node repository. I will just show you some nodes. You just click to IO. This is how it comes. Read. All the reads are here. Excel reader, CSV reader, line reader, table reader, fixed with 5 reader. So all these reads are there. Image reader is separate. It comes in your image analytics extension. It doesn't come here. This is the normal thing. I'm just showing you how it looks. Right. All these modules are there. Come to others. You will see all this. Now come to analytics. I am just giving an overview what all can be done, so that even if you want to do some other work, you can do. Come to analytics. Come to data mining. Here all these are there. Base classification, clustering, rule induction, neural network, decision tree. So if you click this decision tree, you get more depth here. That gradient boosted trees, random forest. Within gradient boosting, you click one more, you get classification. Classification is when your dependent variable is a category, and regression is when it is a continuous number. Within classification, you click one more, you get all this. Gradient boosted tree learner, then gradient boosted tree predictor. So this node, what you do is, if you want to take this node, hold the right button and then move it there. That's how you bring that node to the, this is called the viewer, or the, what we call the browser area of this. So this is how we bring it there. If you want to bring this neural network node, multi-layer perceptron, put it here. This is how you get, and join these nodes. This is how we create a workflow. I just joined the output of this node is becoming input to the node, and this output will go elsewhere. This is how we create basic workflow. Sir, some questions are there?
So no questions as of now.
Okay. This is how we create the workflow. I will just delete them. Otherwise, it should not execute. It doesn't execute. Anyway, for safety, I am just deleting it now. Now, when you come here, you see what is called this KNIME image processing. Under this, you will have all the nodes related to your pre-processing and other things. So click this one. IO, click this IO. This is how it is. You have this image reader. This reads the image. Image reader table. This is an internal format of 9. So first time we don't use this. Image writer. So if you want to take it to some other graphic view or something, you can write the image. Image generator means theoretically you can generate the image like if you want to try some new algorithm, you can say generate the image, black and white image with 30% noise. Now again, generate the image with 40% noise. So you can validate your algorithm, how good it is working for a picture with 30% noise, how good it is working for a random picture. So that is your image generator. So for your research purposes, if you want to try some image which is not still there now, you can do it. Now come to images. Here you get all that pre-processing. Click this one. Here it is. Binary images are black and white images. Filters. Come here. These are all the different filters. Gaussian filter, max filter, median filter. Now, what happens is when you click this one, you get the help on the rightmost side. Here you get the help. See here, this is the help for this particular node. You click this max filter, you get the help for this max filter. You click this average filter, you get the help for this. So whenever you click it here, your right hand part last window has this. So this is your help file of this Sobel filter. You click this here, you get Sobel filter. Now we will come to miscellaneous. Here are all this. Compare segments. This is what somebody was asking me. So you can compare your theoretical segment with the segment in the image. You can say delete this segment. That is your segment comparison. Data row to image. If you have a matrix in the digital form, you can convert that to the image. Here. Process. All this. Image calculator, cropper, intensity pinner, all these are here. Image thinning. See? So many nodes are there in this image processing itself. About, I think, 70 to 80 nodes are there in this pre-processing. Most of it is pre-processing. Spot detection. This is where you detect that salt and a pepper type of noise and then remove the noise. Image converter, image resizer, labeling, image splitter. These are all image processing nodes. This is the feature somebody was asking. Image features, properties. These are all the features thing. Image views. Image viewer, image segmentation. Here you can view the images. These are all the total pre-processing nodes that are available in the picture in the image processing module. So we will proceed. So this image reader, I will just show you. I have already run it. So I will just show you. See, whenever you go to any node, you click the right hand button of the node. So that approximately tells you how to configure the node. So
sorry to interrupt. Question saying, can you please show once again the NIME image processing? I think that's what you're doing.
No, I am showing now. What does he want?
No. So this came from Sangeeta. She's asking, can you show once again the NIME image processing?
No, image processing module, how to install
or how to use it, sir?
No, use it I am showing here. I have not come up with a step. No, we have not come.
Okay.
I am just giving some overall thing because so many modules are there. I may not be using all the modules. I was just giving them overview of how many features are sitting in this.
So Sangeeta has refreshed. She's saying how to install.
Oh, that I will show you. That's what she come to file. Come to install extensions here. Click this one. It will scan and give you what are all the modules that are already installed. It will give. Now come to this image processing here. You are seeing this here. Click this one. And then go to next. It will do it. Since it takes about 25-30 minutes, I don't want to waste time. I am not doing it. Otherwise, this is the way to install. Just ask her whether it is clear now.
Yes, it is clear.
This is how you have to do. Come to install extensions, click it. Then all of them will come. It will scan first. Automatically NIME scans. And if it is installed, if you try to install, it doesn't do it. It will again come and back and tell you it is already installed like that. That's why. This is how we install. Now, for each node, you have to give certain settings. That's called the setting of the node. This is the image reader. So this reads images in the JPG format, JPEG. There are 4 or 5 types of image formats. It will read all those formats. So now you right click this one. You put this, click this configure. Like this it will come. So what happened is the folder. I have created a folder called color images, and I have put 3 color images in this one: img1.jpg, img2.jpg, im3.jpg. This is the folder in which you have put your pictures. Some additional options you can use here. What you do, you select this. There is something called array image factory. So what this means is it will store your picture in that 0 to 255 format as integers. It doesn't save them as floating numbers, because if it is floating, it will take much more space. So normally you select this array image factory. Pixel type is automatic. It will decide whether it is a JPG file or JPG4, all that it will decide. Read all. It will read all the images. If you have grouped them in your folder, it will read those groups also. That is what it is trying to tell. You just put OK for this. So what I will do, I will reset this node. Since the node is already run, I will reset me so that I can run it again. Now, after you do this setting, what happens is you get this yellow light. This is called the traffic light. So when once you see this yellow light, that means you have done the setting for that node and the node is ready to run. So when you see this red dot here, red circle, that is something like a red traffic light. That means some setting has to be done for this node and you have not done that one like that. So that is what this red is. When once the node runs, this yellow will turn to green. That means that particular node has run. If there is some problem with that node, what happens is it will become red again. It will go back. And when you take this mouse pointer there, some small error message it gives you. If that is not enough, there is a log file here. I will show you afterwards. So the log file gives you the detailed error messages. Now we will read the image. Now what you do, you click, then normally you put this execute. Now this has become green. That means the module has run. Now you just click here, view the image viewer. Now you can, these are the 3 images I have taken. There are a lot of noise in this. You just see here. There are all these white noise and then pixels like that. This is very unclear at all. This last image, this img3.jpg is doesn't have much adjust. This is a little bit better. And this also has noise. This is my input image. So the default is this image. This is the column heading it gives when you read it from the image viewer. Now what I will do, I will split them into different channels just to show you how a black and white version of this looks. Configure XY. This is not a 3-dimension image, so Z don't click it. So it is a 2-dimension picture, what I have read. We don't have any sequence of pictures, so that's why this time information is not there. So if it is a moving object, then the time information also will be there in the picture. Like it was taken at 10 o'clock 15 minutes, 10 o'clock 20 minutes, 10 o'clock 30 minutes, 10 o'clock 40 minutes. If you want to analyze some of these games, football game or cricket game and all, then this time comes into picture. Then this will become green if you have time in those pictures. Since I don't have time, it didn't tick this part. Most of them you leave as default settings. we will execute the node. This node has executed. I will open the view now. These are the black and white pictures. This is your red channel. This is the green channel. This is the blue channel. So when you combine all of them, you get back that color picture. This is what we mean by channel separation. Now, if you look at it, if you take this first picture, you don't need this channel at all to analyze. See, why do you want to load your neural network with this G channel? Why do you want it? You don't need. You straight away you can remove this channel and then analyze, give it to the neural network only these two channels. That is good enough. That means you saved lot of time instead of dumping everything into the neural network. See, this hardly contains much. See, these two are good enough for me to analyze. Why will I take this? This is R, this is G, this is blue. So I can, during pre-processing, I can select only one picture out of these two rather than asking the neural network or convolution neural network to analyze all this. And here, this picture is good enough for me. All of them almost contain similar information. So instead of taking all the three pictures, you take only one of them. That means I reduced the processing time like anything. And here also you can take one. Why do you need all the three channels? Because more or less, they are giving you more or less similar information only. See here. Somehow, most of us have a tendency to dump these pictures to that huge neural network, putting large convolution layers, layer 1, layer 2, layer 3, layer 4, layer 5, how many neurons? Simply, we made the network complex. So by separating the channel itself, I can reduce the processing time. Why do I need this picture? Out of these three, one is enough for me. I don't need those two channels because more or less they are containing the same information. It is not containing something different here also. So I will close this one. If you want, you can rename these columns. He called it some, IMG1, IMG2, that you may not like it. There is something called a column rename configure. Here it gives, I am calling them red, green, blue. Otherwise it was calling some IMG, min, comma, comma. These are the default names. So instead of that, you can give it another name. If you want, you can call it red channel. If you want to call it red channel, put red, put underscore channel. Like this, you can give your own name so that it is more meaningful for you to read. Green, underscore channel. So that means it underscore Obama, underscore like that also you can put. Blue, underscore channel. Like this you can do. Put OK. Now this has become yellow. That means the node is ready to run now. This color has become yellow. Now let us execute the node. Put this execute. It has become green. Now if you open, you can see those column names now renamed table. Now you can see green, blue, red, like this it has become. Otherwise it has put its own name, some IMG, bracket, all that was name, because you will get confused later on. So I have renamed those things. Close. I have renamed the column. Now image to data row, this will convert, this will show the data in the numeric format. Like that 127, 242, this is that node. Configure. All the three channel, I want to see how the numbers are. So I am calling it image data. That was original image, this is image data. That means you will see some numbers now. Execute and open the views. You will see here the numbers. So here for this particular image, in the red channel, the minimum something like 30, he has not shown all. He has shown some sample numbers here. This is how they are looking. In the red channel, you see numbers like 34, 18, 255. And in the green channel, you see numbers like 47, 33, some 255. 255 is this white noise, like this. So this is how it is. So this gives the numerical representation of this pictures. I will close this one. Image normalize. So this is what I was telling. So what happens is, if you have images of different sizes, like 1024, few images may be 512, few images may be something like 256. We want to normalize. So before you do any deep learning, you will have to normalize the image. So that's what I am doing here. Here most of them are same size, but still I will show you the node. Configure. There are two types. One is what type of enhancement you want to use. Your equalize, normalize, there are three methods. I will show you one or two methods so that you can see how the image looks after normalizing. You put OK. I have chosen equalize. These are the three methods. What happens is, I think if you want some theoretical background, I will send one preliminary book on computer vision. You read that one. Probably that will give you a better idea. What are these things? What do they do? Like that. I will run this node. Execute. Now you see the difference here. Will you expand this one? This is your pre-processed. Channel normalized. This is the channel. Since here we were not having different size pictures, you may not see much difference. This is your red channel normalized, your green channel, and then the blue channel. So here, that's what I am telling you, can choose only one channel because these two are looking more or less similar. So for your processing, instead of taking so many channels, you can pick up only one. That's what I was trying to tell earlier, instead of taking all. Since the size of the image is the same, we are not seeing much difference. Otherwise, if you feed images of different size, then you will see some difference here. Some few images of 1024 by 1024, few images of 512 by 512, few images of some 256 by 256, then it all gets normalized to one size. Close this one. That is this image normalizer. Then we will come to this global thresholder. This is what he was trying to tell. So I will open this node. Configure. Now instead of that, I will show you the other configuration. Suppose instead of equalize, we go for normalize. How it looks. Put OK. Put OK. Run this one now. Execute. Now you see. This is if you use the other option. Here you may not see much difference because most of them were of the same size. But still you can see the difference here. See, this image looks much better here compared to this. Not much difference. I'll close this one. Now this thresholder will try to remove some noise here. So I will come to this thresholder. Come here. Open this one. Configure. Column selection. What column you want to threshold? So you can select one column if you want. So what we will do? I will select one of the columns. Some blue channel, a red channel normalized. What you do? Move all of them here. Whatever you want to analyze, you put only that one here. It comes here. Green channel normalized. If you don't want, remove it here. If you want to take red channel, move it here. So on the red channel only, I am applying that thresholding, not on all the three channels. Append means it will append the picture. It will not overwrite the picture. So I am calling it normalized threshold image like that. Or you can give a name like this. I will show you how to give the names. Thresholding is global. You can give red underscore channel threshold, THRS, you can call threshold underscore global threshold. There are many methods of thresholding. You call it global. Now you put OK here. Now run this node. It will append. Execute. I will open this one. You can see here now. After thresholding, you can see the difference here. So what has happened is, some of these white have become dark, dark have become white. It is on the red channel I have applied, not these two. Here. I took only the red channel, this picture. This picture. We will do some smoothing here. So on the normalized picture, what I am doing is I am doing a smoothing filter. So it will try to remove the noise and then smooth the picture. So come here, come to configure. So which column you want to smooth? It is here. I have just taken all the three so that you will see all the three of them there. Column suffix, I am calling it normalized, threshold, Sobel filter like this. So here I did it for red. You can do it for red only here. Red channel, normalized image, you can put. Options. This will tell you the border what to do. What happens is when you go near the border, you may not have enough pixels to do it. So how do you want to fill the border is here. Then the convolution method, there are 2-3 methods. I don't have time to cover. We will take one default method for your demo purposes. Column selection, I am doing this red channel normalized image. Now you just run this Sobel filter. You will just say execute. Now I will show you the picture. See here, it has smoothened. Red channel is here. Nice image has come down between the two, between this and then this. These two I have not smoothened. I have smoothened only this one. Close this one. After filtering also you can put the threshold here. Because not all the columns were selected. That's why. See, this is how you get an error message. See what happened, I did not select the columns. So what happens is when you move it here, you see some message here, invalid column selections, all columns are not selected. So what it means is earlier I had all columns. Now what I did was I selected only one column. So that's why it is trying to tell that it's not, you have not fed all the data like that. Some discrepancy is there between this and this. That is what it is trying to tell. Here I have only one input. Here what happened was you had all the three. See here all the three are there. That's why. I took only red channel. So what you do, you put here, take only a red channel normalized image threshold that you put. You put OK here. Now you run this one. Put execute and open the views. It will run. See here, this is the red channel, filtered. This is your image features. So let us see what it gives. It will tell you what are all the features. This first order statistics, it will give you that mean, median. These are some of the image features. This is what we extract using that convolution or those type of neural network. So I will just run it, this first order statistics. Put OK, execute. It will give you some mean, median for the image one. Minimum grayscale is this, maximum is this. The mean grayscale of the picture is some 64.44. This you leave it. Standard deviation is 60. Variance skewness 1.46. These are your basic statistics. And your quantiles are also there. Quantile 25. What are the? This also you can use it for thresholding. Some of you are asking, you know. So you can put that quantile 75 as a threshold. So all the pictures above 88 will go to one type of color, and all the pictures below 88 will go to another type of picture. This is one method of thresholding. You can see the quartiles here, 25, 50, 75, median, like that. So if I put the grayscale of 88 as a quantile, so what it does is all the gray levels greater than 88, you will become white, and all that below 88 will become dark. So for all the three images it has given. This is your image number 1, image number 2, image number 3. If you see here, most of the data is normally distributed. You see this skewness here, it is roughly some 1.44, 0.256, 0.42. That means it is virtually a 0. In real life, you will never get a 0. So what it means is most of the grayscales are normally distributed. That's what this is trying to tell. And there is not much difference between the mean value and the median value. This difference is coming because some noise is there. Because of the noise, your median value is 139, mean is 145, and median is 103, 104. So second picture, not much noise. Compare the mean and the median, that will give you some idea about the noise level. Here the mean is 64, median is your 50th percentile, it is 55. So this is little bit noisy. Whereas your second picture, there is nothing much. We will close this one. That is your image features. There are different type of filters. One is a bilateral filter, the other one is a median filter. This median filter I will run. So that will be a little bit different from this Gaussian filters. Then I will show it on a color image. This is a black and white image. Then the same thing, I will show it on the color. See here. This is the median filter. After this, you can put a threshold so that this noise gets removed. We'll show you on connected component analysis, how you can get it. There is a thresholder, then I will run this node. You can see some of these segments here now. This noise we will remove afterwards, don't worry. So what has happened is you can see some large segments here. In the original image, it is like this, something like this. It has grouped and then brought you some broad segments like this. Here there is one segment, another segment, another segment, another segment like that. Here also it has brought. See here, these are some major regions. These will become some of the features. That is what we put a rectangle here and then put it as one feature. This will be another rectangle. Person one's face will be another feature. This will be another feature. Here you can break them. Put one rectangle here, one feature. Second, third. There are 4 segments in this. The segment area and the standard deviation, mean, median, that can be computed for this segment. They become the features of this. These two I have not used. That's why nothing has come. I didn't use these 2 images. I used only one image, one channel I have used. So this is how the segment, this is a black and white image. I will show you on a color image later on. Because most of the time you can manage with black and white, then what happens is your computation power is less required and your execution will be fast. That's why. You can give labels for these segments also. This is the original picture and that's the segmented picture. Something like this it has become. See here. Some regions have become larger regions because there is not much gray level difference between these two. So what it did was it merged these regions. There is a big difference in grayscale. So those regions have been left as it is. Best thing is you play around these pictures. That is the best way to learn. No amount of my telling will work. They the best way to learn. Take some images. There are large number of images on Kaggle site. There are quite number of images on your gov.in. That government site is also there. And you can go to any e-commerce site. There are large number of e-commerce shops. Start downloading some of them and save those images. TV, mobile phone, fashion goods, all are there. Shoes, accessories, all that. Store some 100 or 150 pictures. Then start doing all this. Then you will learn a lot. And it will help you to train your neural network faster. And at the same time, your classification accuracy also will be higher by this. Otherwise, what happens, if you directly feed the picture, you see here, it will start identifying so many segments, and even if there is a small difference in this, it will misclassify your image. Whereas here, what happened, we merged all of them. This became a bigger one. So here the error will be less. See here what happens if you directly feed, that convolution neural network will extract this also. So in your training picture, it may be there, but in your test picture, this may be a little bit different. Then it will say, it will misclassify. Whereas here, after pre-processing, you see here, misclassification is less here because the whole area became large. Shall we continue? Yes, or if some questions are there, if some questions are there and this black and white, they will answer no, because the moment this picture goes away, they may lose track.
I can see one question, which is how to remove channels and consider only one amongst 3. How to remove channels and consider only one amongst 3.
There is a row filter, there is a column filter. So that you can use. Otherwise, here I selected only one channel. I will show it again. Let me close this one. You just come here. All the 3 columns are there in this. Red channel, green channel, and then blue channel. All the 3 are there. When I come to image normalizer, you open this. Column selection here. You remove all of them. If you want to select on the red channel, click this and then move it here. Now you put OK. Now only that one channel got selected. There is a column selection is there, highlight that column selection. All the available columns will come. Then what you do is push all of them to the left side. Then what you do, click only the one you want by holding this mouse button, shift it to the right side. Those channels only will be used for further processing.
Okay. Sir, another question is, if we see two or more images better or similar to be taken for the process, do we go by the image data to pick one?
Correct. I separated the channels, you know, I showed 3 pictures. By looking at that, you can filter visually itself. That's what I'm telling here. I will show you here. We split it into 3 channels. I will show this output. Now you see, these are the 3 channels. Now what is happening if you take this image 2, more or less all the 3 channels are carrying the same information. There is not much difference. So pick one of them. Either you can take only the green channel or you can take blue. Then when you come to image 1, this channel is totally useless. It is all black and not much discrimination at all. You take this image. So we can filter only red channel for image number 1. Then you can use a blue channel for image number 2. For image number 3, you can select any one channel because I am not seeing much difference at all among these images. So I reduced it now. So for picture number 1, instead of taking all the RGB, take this one. Here you take this one. It doesn't matter. Here, little clear. Here you take any one. Almost all of them are on the same size. That is what it is.
Sir, the next question is how the value or parameter for threshold has been decided here for global thresholder.
Global thresholder automatically uses. I will show you. What happens is, just where is that one? You click this global thresholder, you get an help file here. You just read this help file. Here he gives. This whole text you will have to read. The little bit of algorithm or the way he is doing is put here. See here. It is here. Whole thing. How he is doing, he has put here. Roughly he has given which algorithm he has used is also here. Now what has to do is you go to Google and then click this algorithm name. You will get the algorithm. There you get the detail how this global thresholder did. See, when you click this, you will get the help file. A brief help file will come here. Then in this help file, if required, they will give you which person's algorithm or which paper they have referred. Now you can go to Google and then put that author's name or something. Sometimes here itself you can click. For some of the help files, you can click here itself. For some other help files, what has to happen is they will give you some names here. Refer some paper of some XYZ person, like that. That's what you have to do. See here, the entire process is here.
Sure, sir. Thank you. Geeta is requesting to show the last step once again, sir.
Which last step? There are so many steps here. Can you ask her?
She's asking, she has this specific question. In large database, how do you filter and select one image with channel?
See, this is, I will show you. This is the database of all the images. See here. All the 3 images are there. Now, if you want to select only one image, there is a column selection here. You come here. You have all the columns here. All the 3 columns are there. Now, when you go to the next step, all the 3 are read here. Now, when you come here, for example, column rename also, I am doing all. If you don't want to do all, remove. If you put this remove, it will go away. Those channels will not come. See, there is something called remove. So if you remove, for all the future, only one channel will be there. These 2 people will go away. That means these 2 images will not be there further at all. When you click this remove. Here, everywhere he has put remove. So when you click this remove, for all the further processing, this will not be there at all.
Sir, she is also asking, in a large database, is it manual?
Which one? Last database means? Which is
In a large database, is it manual?
No, large database, yes. It may not be manual. See, what happens is, some of them you do manual. For similar pictures, I think automatically it will do it.
Okay.
Some picture, after all, it is something like giving a ground truth for the analysis. So unless you give, suppose if you want to classify defaulters and non-defaulters, let us say you have some 20,000 customers. So what I will do, I will use sample of some 100 customers default, 200 non-defaults. By using them automatically, I will be able to somewhat identify who is default, non-default.
Okay. Sir, I think we are done with the questions. I do not see any further questions. We can proceed.
Okay. I will show another worksheet now. We will use that color picture now. Just use. I will show this one. We will do the dilation and other things. I am going to remove some noise, smoothen the picture. It is the same data. I will show you the data. It is the same images I am using. One image only I have taken here. I have not taken all the images. This fruits and vegetables image I have taken. Now I am going to smoothen this picture. I have run the Gaussian convolution. I will show the output of this. See here, the picture is smoothened. Do you able to see the difference? See here, you have lot of these dots, which is a noise. I have run a Gaussian filter on that. So most of the noise got reduced here. See here the difference between the two. So we have, to some extent, we have reduced the noise. It is this filter, this step. Configure. Sigma is 1. I will change it to 1.5. You can see the difference here, how the new picture looks. 1.5. Put OK. I will run this one now. Gaussian filter with 1.5 standard deviation. See here. It is looking a little bit different now. Earlier I used 1.5. I will do it 2 now. You can see how the filters work. Some learning has to take place before you do full-fledged computer vision on large number of images. Some basic learning has to happen. You change it to 2 sigma. I will just show you the new picture, how it looks. Run this again. Now you can see here. It has become blurred, but at the same time, noise also has reduced. See here, noise has reduced. I will do it with 1 so that you can see the difference. Configure. We will make it 1 sigma. Border column selection. We will append the column. I am going to show you both the pictures. GC 1 sigma. 1 sigma. I will run this one. This is with 1 sigma. This is 1, that was 2. So if you want to see both of them, what you have to do is you will have to do this image joiner here. See, there is a joiner node. With that joiner node, you can join both of them. That is how it is done. We will continue with this 1 sigma. Then here we have something called morphological operations, that is image dilation, open, close, what I showed in my PPT. I will show you some operations. We will say configure, four cornered, column selection, here image, dilate. I am dilating the image. What do we mean by dilate is here. Grows brighter areas. Here. See, what do we mean by dilate? Grows brighter areas. What do we mean by erode? It shrinks brighter areas. So if you have small, what you call salt type of noise, you erode the picture. Then what happens is that bigger region will become small, and at the same time the small fellow will vanish. That is what it is. Grow bright areas. So bright areas will grow, then your black fellow will go away. This is a dilate operation. I will show you now how it works. Put OK. We will run this one. Execute. This is a dilated picture. See here. See here, this noise has got reduced. See, in between, you are seeing some noise like this red color and all, that has gone here. It has reduced. And here, you are seeing these small things here. See here, some small lines were there. It has become one region here. See here, within this also there was something here. So that has gone here. Here also there were many circles. These dark regions, it has gone. This is your dilation. I will show you the other operation also. This is second operation. Configure. Here we are eroding the picture. Shrink brighter areas. That was grow brighter areas. This is the reverse of that. Shrink brighter areas. You put OK. Put apply. Now we will run this one. It is the reverse. We have joined both the operation. I am selecting some columns here. Then last node I will run here. You just see here. Now you see this node did not run. I changed that name, you remember. I changed that name. So it says there is no image column like GC image dilate like that. You remember I changed one name here. It became a different name. So what it is trying to tell is you just come here. Configure. So it is called image GC 1 sigma image erode. So what happened is one of them is not here. That is what it is pointing here. I'll just show you what it is pointing. How to remove some of these messages. Image GC image dilate is not there. So that column is not there. This is not there in this. So you remove this one because that column was not there in that. That's why it didn't run. Now let us try to run this. So what happens if you do not correct the error in one segment, it will not allow you to go further. See, the subsequent nodes will not run at all if you do not correct. That is what happens here. Here you will have to correct that. Push this one here. This image is there. You can remove these two images. This is how you will tell how to correct some of these errors. Still I may make an error. What I am telling is I am just telling you how to correct those type of errors. Execute. Here you try to configure. Okay. There is no such column. So if you do not have those columns, you will get like this. Then what you do, you remove this equation, put these two only, because this is the column I have. Put minus the other column. Great. Now you run. You can see some edges here now. See here, I have created the edge map. Using dilate and then erode, you get the edges of the picture. See here, I have only edges. This is how we do that edge detection. Transpose means it will just reverse the picture. You will get like this. Hello? Good afternoon, Andy. Saturday. No, now 10:30. ಏನ್ ಬೇಕು ನಿಮ್ಗೆ? ಕರೆಕ್ಟ್. ಆಗ್ಲಿ ವಾಯ್ಸ್. ಓಕೆ. ವಾಯ್ಸ್. Okay. Bunny. Okay. So this is how we have extracted the edges. See, all these edges have come. Now you can put this marker rectangle and then you can say this is some fig or something. Now here you can say this is your lychee. Like that you can label the image. And that labeled image you can give it to the classifier now. That is how it is done. And your CNN also will extract these features only. So what you do when you automate, instead of doing this type of workflow, we will do it in the convolution neural network. It will try to extract exactly this. So what I was trying to do was, if you give this pre-processed image, there you will be doing less work. Even in one stage, convolution neural network itself will do it. Otherwise, all these would have been done internally there. Then your network size increases and your execution time will increase. That's what I was trying to tell. This is what we call the edge map. You can play around this. I will send this data and then workflows also to you, so that you can play around with different type of these morphological operations and then see. Then there is something called edge gradient. I will just show you how this is another way of getting the edges. I don't know whether I have configured this or not. Oh yes, it is there. Image 1, image 2. Image 1, I will show you the edge. So if you want to run the last node, what you do, you don't have to run all those previous nodes. You can just right click and simply say execute. I think somewhere it says I will have to reset this node. Reset. Now you execute. That's the edges. I have colored them. This is the edge map. First image only I have done. This is how the edges are looking. These are different segments. You can label those segments now. And that labeled segment is what goes to train a classifier now. So if it is able to find these objects, it will classify, okay, this image number 1 contains fig, it contains lychee, it contains some other fruit, 30%, 40%, like that it classifies. So there is a way to give labels for these segments. There is something called a segment labeler that it does. Due to shortage of time, I won't be able to show all that. Maybe some other point in time in future, we will do some one-day program or something. Then you can also load NIME into your machine. Then this will be more meaningful. But otherwise, you see what type of output I got. We have got these edges, and this is the workflow. This workflow I will send it so that you don't have to again draw this workflow. You can run from this. The quantile filter is what I have used. You remember I was telling? It will smooth. There is a thresholder, image converter. This converts that to the number. Then the filtering I have used. Then afterward there is some morphological operation also I have used. Here. Dilate. Same Sobel filter we have used. It is an edge detection filter. The Sobel is basically an edge detection filter. So the outcome is this one finally. This will join. There is an image joiner. So what happens is it will join both the columns here. Both the columns it will join. From your left image and then right image, it will join. Some output has come from this. Some output has come from the second Sobel filter. We have combined both the columns. That's what it is. Is clear? If you double click it here, you can see all the examples that are there in the KNIME hub. Just show here, all these example workflows are there. Community, if you click, you will see all this. Under image processing, you have a lot of these examples, tutorial, integrations, applications. Under tutorial, you click, the node tutorial is there. Within that, you need all these basic views, table creation, dimension selection. So what you do is you click on this workflow, then automatically it comes here. All these examples are here. I'll just expand this a little. See here, interactive annotator. That is how you annotate the segments. All these are here. Application tutorials are also there. How to mask, highlight, how to extract RGB images. So many workflows are here already. This, let me see if I can, what I will do, I will show one PPT which gives you a little bit of background of the deep learning. These are all pre-processing. Let me see, yes. What the neural network does is, it will do some type of a nonlinear transformation between the input and the output, because these images are complex to analyze. We can't use some linear regression or simple decision tree to classify because the data structure is somewhat different. So it uses what is called a neural network. Neural network tries to approximate the way our human brain functions. Though we cannot replicate it 100%, we are able to replicate as much as possible. So neural network has three things. One is called the input, where you give the input. There are some hidden layers in the neural network. They do some type of a mapping, some type of transformation it does on the input data. Then eventually there is an output. Now what we do, we compare the input with the output and then try to reduce the error. That is your basic neural network. And convolution neural network is somewhat, we put more layers in the neural network. I don't know whether all of you had some idea of neural network or not. I can send some material, because if I start explaining neural network, this convolution, I will not be able to show. So what happens is, convolution neural network is a neural network of multiple stages. And the concept is, at each stage, we learn something in that image. That is the concept. First stage learns some features in the image. That first stage output will go to the second stage. So based on the second stage, we'll learn some more features. Based on that, it will go to third stage. So third stage will learn some more features from this first and second stage. So like that, normally we put 3 or 4 stages for this complex network. And eventually the last stage contains somewhat an aggregated information of the picture, like that edges what I showed. Now that you will feed it to a fully connected neural network, and it will try to classify. That is the basic idea. Because CNN itself will take 1 or 2 hours to cover. So I have briefly told and show some PPTs and then see whether a workflow I can run. So what we will do this digit classification. This is your classical MNIST digit, where you have numbers from 0 to 9. We will train a neural network, and if any new number is given, it will classify whether it is 9, 6, 7, 8, 4, like that. Since it is a black and white image, it is little easy for me to train, and then it takes little bit of less time. So what is happening, we have these 60,000 training example. These are 28 pixels per 28. That means each rectangle, horizontally it is 28 and vertically also it is 28. So like that, you have 60,000 training samples. So on these 60,000, we train the network. On these 20,000, we ask it to classify. And let us see how good it identifies these digits. Here, the same one is written in a different orientation. See here, it is somewhat inclined, whereas here, it is not inclined. So 3 also, there are different type of 3s that have been written. And 9 also, see this 9, this 9, this 9, some, and again this 9. So it will learn the way different people write handwritten digits, and then we will classify. See, this is how the convolution neural network looks. All these you will have to do, the settings you will have to do it in that either in Keras or in the deep learning 4J network. So what is happening is, this is your input image, 1 into 28 into 28. We put a kernel. You remember I showed in one of my PPT that center pixel will be replaced by a combination of these 5 by 5 pixels. So what happens is, this 24 is getting reduced now because each 5 we have put only 1 pixel. So what is happening is, you get 6 layers like that. Each layer will identify some features. Different features will be extracted from that. That is what has come here. So in layer 2, some reduction has taken place. This 28 has become 24. Now this 24 has become 12 because we are using different filters. and each filter will try to reduce the size of the image, and 6 features we will extract. From each of these digits, we extract some 6 features, either their orientation, average image size, the size of the image, those things we will extract. So, and next stage, it has become 8, and last stage we have made it 4. So your 1 into 28 into 28 size image has been reduced into 4 by 4 into 12. See the reduction, it has already reduced. Something like 400 has been reduced now. And finally, we connect it to this fully connected layer, and your digits we will feed here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are those 9s. So when you feed 9, 1 gets activated. When you feed 2, 2 gets activated. When you feed 3, 3 will come here, like that. So what I will do, I will try to load this workflow. I think somewhere it must be available. We will go to this 9. Let me search this one. This is what you have to do. There is something called a DL for the model reader. We have these layers. This convolution layer is there. Auto encoder layer is there. The perceptron layer is there. Let me see whether I can locate those workflows here. Somehow that workflow I am not able to locate. No, somewhere this browser is getting stuck. I don't know. I'm not able to load that workflow. Somewhere it has got stuck.
So any suggestion how to
Somewhere it is getting struck. It is not coming here. That is why.
okay.
It didn't load. Somewhere it is getting stuck in this thing. Show one of them. If something loads, I will show. I will just open some of the nodes and then show. I think at least it will give, even though it doesn't run.
Sure.
Just show. Somewhere it is getting stuck. So what basically we do is we put these convolution layers. I will orally tell. Somewhere it is getting stuck. I don't know. It is not moving. So what we normally do is we do the pre-processing. You can select the channels. Then inside the convolution neural network, instead of running that Sobel filter, median filter, what can be done is there are equivalent convolution filters. That is what you put it in the convolution layer. Normally 3 or 4 convolution layers are enough. That will reduce the size and it will extract the features from the image. Then the last stage will be that fully connected neural network where all the input gets connected to the output. Then the output you feed the class also to what class it belongs. So then the network gets trained. You will go through some 1000 or 2000 iterations because first time it will make a mistake. For 1 it will classify as 2, 2 will become 3, 3 will become some 9, all that will happen. So when enough training data it sees, the error will come down. So when once the error comes down, you split the training data into 2 parts. One is for training, the other one is for testing. So you validate it on that, then you deploy it. I think that is the best I can do. Maybe some other time we will have another 1 hour or 2 hours class where I will exclusively cover the CNN part, because combining pre-processing all this, it is difficult in these, even in 4 hours also. It takes some amount of time. So what we will do is, instead of doing that half and then nobody learning, we will hold some other session. I think Sudeep, I will tell him. So we will teach exclusive. You have seen some pre-processing operation, how to remove the noise, how to identify the edges. That part, edges are the features. So what we can do is from that point onwards, we can feed it to a learning network, a feed forward type of neural network. Then with that network, we will train. After pre-processing, it will go as an input to the neural network. The neural network we will train. Then when any unknown when an unknown picture is given, it will extract these features, same features. It will go through what we did in the pre-processing. Then it will classify. I think that is how we classify both the digits and then the numbers. The whole thing got stuck, not moving at all properly.
Sure, sir. We can plan
Correct.
for another
That is
session.
much better. So that at least they have some fundamentals now. What is an image? How to pre-process? How to identify the edges? They will become the input subsequently now. So about 1 hour, about 2 hour session we will plan. So that I will show you that
Sure.
CNN network and we will classify those digits. Or some pictures also I will take and then classify. And by that time probably I will resolve that Python conflict also. Some new version has come, so some of these workflows stopped working. That we will correct it. I think that is the best way to go
So
about.
that would be
Yes,
perfect, sir. I think
yes,
that should work.
yes.
And I would request the attendees and the participants to key in their
If
questions,
any
if
general
any.
questions are there.
Chandrashekar is still there for
Correct.
another 15 minutes. So you know, we can use this time sensibly then. Sir, I see two questions. I'll just quickly shoot that. A question from Manisha, who's asking, how do we sharpen image and what feature?
No, sharpening the image is the dilation and that other one. That's what I showed you, you know. From that blurred picture, I extracted the edges. There are 4 or 5 operations. With that, we can sharpen the picture. Edges again, I can see. You remember one color picture I showed where the edges were extracted. All others went to the background. Now, what you can do is you can enhance that picture again so that the edges will become more prominent, because in that edge, all the background has become something like a black and the edges only were appearing there. So what you do a contrast enhancement. So
Got it.
that edge you convert them and read them as numbers, plot the histogram of that number. In that image you will get the histogram. That histogram you can manipulate so that those will get sharpened much better.
Got it. Okay. And I have another one from Pawan, who's asking, can you please share the name of the book on computer vision that was mentioned?
No, I will send it to you. I will send it.
Sure.
It is the classic book we used to teach the course.
Perfect. Perfect. So Pawan will share the name of the book. Any other questions from?
What happens is they have to play with some images and then learn. That is the best way to learn. This no amount of theory is going to help much. It will give you some background, how to put a threshold, what is a dilation operation, what is an open operation, what is contrast enhancement. Those concepts it will give. But they don't have to go into too much theoretical aspect of that. The best thing is take the picture, keep on changing some thresholds and then learn. That will give you an idea. That is the best way to learn these type of courses rather than reading that 400-page book or 300-page book. It is something like trying to learn swimming or car driving using books alone. Irrespective of how many books you read, when you sit in front of the steering, sometimes that whole knowledge evaporates. And then again you will have to learn.
Very true. Sir, Pawan is asking the same question. How can we install and run NIME on Linux, Ubuntu? So I think you had covered this last time in the last session.
Correct. Linux also has a different version. It works under Linux, definitely.
So
I have loaded Windows version. When you install NIME, he asks you what operating system you want to load. There you click that Linux or Unix variant, whatever it is, Red Hat Linux, all that are there.
Sure. And Pawan, you can also refer the last session which we had with Professor Chandrashekar. It's there on our YouTube channel. Any further questions from the participants?
Sir, most of them are working or they are new or what is it? Then accordingly, I can mail some books and PPTs instead of.
I can check that. I can
Okay.
registration information and share that with you. Rajmani is asking, share the link of the previous session. I'll do that on the chat window. I'll share the YouTube link. For everyone, here's the YouTube link of the last session, just for reference. Okay, I see a couple of more questions. Are the same kind of processes used in any kind of images? Example, X-ray or satellite images?
Correct. It is used. We do the same thing there also. It is used. Hey, NRSA Space Application Center, they do this work day in and day out.
Absolutely. And Raghavendra is asking, can we reuse existing TensorFlow or PyTorch models in NIME for transferring?
Yes, it is allowed.
It is allowed, yes.
What happens is he will see, there is a command called freezenet. So you can point it to the GitHub or something where the trained networks are there. So from that point onwards, it goes. It doesn't again reinitialize all those weights and start training once for all. No, that facility is there.
Sir, I don't see any further questions. Maybe we can close this session.
Yes.
Just for everybody's benefit, I'm sharing the YouTube link again on the chat window. Please refer to this. This is for the previous session. We will also upload it for this session, and I'll work with Professor Chandrashekar for another 2-hour slot. I'll invite everybody who has attended this session so that we can continue where we left.
Sure.
And my colleague tells me that, we would also be sending a survey form. That's an online survey form in your email. So when I'm sending the YouTube link, you'll get the survey form. Please take out some couple of minutes to fill that survey form. All right, sir. Thank you again. Yet another great session. We had a little bit of technical issue, but that's always a boon. I would say we get to see you again for 2 hours.
Sure.
So we will have all these participants join you and many more.
Correct.
And we look forward to more sessions with you. And my special thanks to all the attendees who have stayed with us till now. And everybody have a good rest of the day. And thank you so much, Professor Chandrashekar, Supriya. Thank you so much.
Thank you very much. Thank you all very much.
Thank you, sir.
For your patient hearing.
Thank you.